I'm Ed Angel, and it's Dave Schreiner. We've been doing this course in various iterations for quite a few years, and it started off as a basic OpenGL course, and then it was a modern OpenGL course, and this year we're switching to WebGL. So I think there's probably a bunch of you here. How many of you have done some OpenGL? And so, okay, so we'll assume that most of you at least knows the basic concepts, and I'm going to focus on what you have to do that's different when you go to WebGL, and why WebGL is so important, and some of the sort of gotchas that'll come along. So let me give you, just before I turn things over to Dave, let's look at a couple of, why isn't this moving? Broke it already? It doesn't want to go to the next slide. Okay.
So tough to get good help.
Oh, there we go. There we go. Okay. It'll do it. Okay, so we're going to skip over the evolution of the OpenGL pipeline, just sort of stress that you are working in OpenGL. And what I want to focus on, my part of the first half of this, is to go through a couple of pretty straightforward examples, but it'll emphasize the differences between what many of you have done with OpenGL and how you do things in WebGL. Then Dave will talk some about the OpenGL shading language and a little bit of the differences between the shading language and what the version of it that's in WebGL. And then we'll do go through a bunch of the topics in the second half, lighting, shading, texture mapping, viewing, and how you do those things with WebGL. So we'll go through, and the examples I'm going to do, let me do one more, is I'm going to go sort of a sequence of start with something as simple as a single triangle, then I'm going to move up to talking about a cube. But with the cube, I can introduce interaction, and that's one of the things that's going to be very different when you work with WebGL and work in a browser environment, is how you do interaction, is I claim is going to be much, much more simple. Then we'll look at lighting, we'll look at texture mapping, and so I'll go through that kind of progression. So let me bring Dave up, and then Dave will talk a little bit about the basic ideas, and then I'll come back and go through some examples. Do you want this? Do you want to use that?
I'll use that.
Hey, and welcome to SIGGRAPH 2014. I'm Dave Schreiner. In addition to doing this, I'm also chairing the conference, which is going to be fun. This is really interesting technology for me. Just before I dive into this, we're going to do a little use of, unfortunately we can't do WebGL this evening because not all devices support it yet. A little surprising on that part, but what you'll learn here incorporates a lot of interesting web technology. I don't know if any of you have heard about, we're going to try to set a Guinness Book of World Records this evening, right? We're going to try to make the largest image displayed across a collection of cell phones. And that actually will be entirely a web app using the canvas element, which we'll talk about in just a second. I can't use WebGL, otherwise I would have done that, and that would be cool. But we'll get as close as we can, and we'll push the people who don't have WebGL to do it. Otherwise, good stuff. So, OpenGL is a technology that's been around for about 22 years now. It stands for the Open Graphics Library, and it's just an application programming interface, an API, for writing interactive graphics applications. It's not a ray tracer. It doesn't make photorealistic images unless you invest a whole lot of time, but it is the basis for many, many interactive applications, whether they're games, scientific visualization, medical, or world record attempts, as it turns out to be. So with OpenGL, you can make high-quality images. They're not photorealistic. They don't do things like shadows intrinsically. You have to do a lot of hacks to get there. But it's easy to build hardware to support this kind of stuff. And effectively, it's really a great, simple system for taking and rendering 3D objects with computed colors, texture maps, and everything nowadays is shader-based with it, which gives you powerful, incredible computation available to be able to work on your 3D objects to make the right colors and all the necessary pieces. So at this point you go, well, what's that got to do with WebGL? Well, WebGL is a derivative of OpenGL, and it turns out there's actually an intermediary in between called OpenGL ES. The ES stands for Embedded Subsystem. About 12 years ago, as mobile phones first started to be able to have graphical capabilities, they looked around for some API to be able to program it, and OpenGL was in full swing, doing lots of great stuff, but it was too large of an API. At that time, it had about 600 function calls, and a cell phone probably had about 32K of memory. So like we can't support all those function calls, which is probably good. So they took and they trimmed it down and they made this version called OpenGL ES. Well, OpenGL ES has been the foundation of all the kind of graphics that you've been seeing on your embedded devices. And people said, hey, this is really cool. And as web technology has increased, we needed a 3D API inside of there. So they took OpenGL ES, which is a smaller and cleaner programming language, wrapped it up in a JavaScript library and called it WebGL. And so the nice thing about WebGL is it's supported now in all your web browsers. And what's super amazing about that is, you know, Ed and I have been teaching courses on OpenGL for a very long time. The biggest problem is opening a window. We can talk about GL, but, you know, and that's easy. People get it. Opening a window, you know, if you're on a Mac versus a Windows system, or Lord forbid you're trying to do something on Linux, you know, that's really painful. This stuff, one line. We're good to go. So it's really great. It uses an HTML5 canvas element. When you see it, you'll be like, that's it. And indeed, that is all it is. This is super great stuff. I'm very excited. In fact, I've helped Ed convert his college textbook into using this because it just simplifies, allows us to concentrate on the material and not so much on the mechanics, which has always been a real problem. Additionally, all the standard web features that you might be familiar with, CSS, using jQuery or any of the other JavaScript libraries, even Unity and things like that, are available for WebGL. So it's a really rich environment to do this kind of stuff. And these applications are really quite simple to put together. The thing I'm doing tonight is taking me about 2 weeks. You know, before that, I tried to write a native app, and that took me 6 weeks just to get one version done for one operating system. So what do you need to know about this? Well, you need to know a little bit about web environments and execution. How do you set up and write HTML to develop a canvas element? How do you write the appropriate JavaScript to be able to access that element and set it up so that it's capable of rendering WebGL inside of it? And you need to know a few things about modern OpenGL, like the pipeline architecture, which is the next thing that Ed will discuss. What does it mean to have a vertex shader and a fragment shader? How does it fit into the scheme of things? And what is their actual role? I'll continue on a little after that doing some stuff on the shading language, which will be crucial to do this. OpenGL is kind of like send down some geometry, send down some triangles or maybe some points, and everything else is use a shader to figure out what to do with that stuff. And so you'll see shading is a really important part of this. And along the way, we'll show you some of the JavaScript. We'll toss in some elements on interactivity so that you can have interactive applications. Really, as far as a programming language goes, it's HTML, so it's not the neatest of languages. But if any of you program C++, I guess you're going to go like, this is a whole lot better. Anyways, we're off to a lot of fun. So, Ed?
All right, so, okay, so what I'm going to start with is as simple an example as I can give you, which is one triangle. And you shouldn't think it's that simple, because ultimately all WebGL is going to do is render triangles and points. And so it's just a lot of triangles that are going to make up a more complex application. But I want to look at the different parts. Now, one of the things we pointed out in the previous slides is that even though we can integrate with the standard packages like jQuery and CSS, what we've tried to do is keep things as absolutely simple as possible. So we're going to do things using only HTML in a very small amount and use JavaScript and none of these extra things that in practice they're going to make your code much nicer and much simpler. But we really want to focus on what is the minimum things we need to do to write a WebGL program, and that's what we're going to be seeing. So here's a very simplified model of the pipeline that we start with an application. And what's the job of the application? The application is going to generate the geometry, and the geometry is going to be expressed in terms of a bunch of vertices that define whatever objects you're going to be working with, and they flow down this pipeline. Now, OpenGL originally was designed for a pipeline kind of architecture where we process a vertex at a time. But as hardware evolved, what we got is shaders that were in the middle. In particular, we got programmable shaders in a graphics processing unit that allowed us to decide where we were going to carry out the operation. So initially, we would do everything in the CPU of the computer, or at least that was an option on basic implementations. Then we started carrying out those operations in shaders, but the shaders were fixed function that we couldn't really do very much with them. But now now they're fully programmable little computers, and so that's really the key to being able to do the kinds of applications we want to do, and do them very, very rapidly. So the model we want to start with is you have an application, it generates vertices, those vertices go into the vertex processing unit on your GPU, and you load a program in, which is your vertex shader. The output of that vertex processing are vertices that may have had some things done to them. They may have changed their positions to be in a better coordinate system. You may also have generated or processed colors or your shading model there. And you output a number of variables which go to the rasterizer, whose job is to produce primitive pixels or potential pixels that we call fragments. And by interpolating the values that come in from the vertex shader, each of those fragments then generates an instantiation of a fragment shader, which you again program, and eventually pixels will come out. And so in every application, and you have to have three somewhat independent programs. You must have a vertex shader, you must have a fragment shader, and you must have your application shader, your application program. So for those of you who haven't been familiar with modern OpenGL programming and still use the old fixed function pipeline, it's mandatory that you do these things now. There are no more default functions, there's no more default shaders, and most of the functions, if you've been doing fixed function pipeline, have been deprecated, meaning they're gone. So this is the basic model, and we say, well, what does a WebGL program have to do? Okay, it has to set up an HTML5 canvas. That's the thing that we're going to render into, and one of the nice features of this that makes it all work so well within the browser environment is other web applications can also render into that same canvas. It's not just something that's under the control of WebGL, it's actually part of that whole browser environment. Then we have to generate, as usual, generate our data in the application. We have to write a vertex shader, we have to write a fragment shader, and we have to get the data over to the GPU. Because what we're really trying to do in terms of what the CPU is doing, it's really trying to just set everything up, because the work is going to be done on the GPU, because that's where the fragment shader is, that's where the vertex shader is, and that's where the processing power is. So the big part of what we're going to see in the code is our effort to get the information out into the GPU and then connect everything together, because you've got these three separate programs. We have to link that all together. And finally, which will actually be very simple in the program, is we say, go, render everything that we've sent out to the GPU. So we'll see that in our example. We're going to use the HTML5 canvas element, as we've said. The way we're going to do things here. Now, there are a number of ways that you can organize your code. I've chosen, and we've done this in the book, is to say what we're going to do is you have to have an HTML file. You can put everything in the HTML file. Every browser understands JavaScript. We'll say more about JavaScript as we go along. But what we've chosen to do, I think, is to put all the setup stuff in HTML, opening the canvas, specifying parameters, getting your shaders, and then all of the action, generating the geometry and rendering it, we're going to put in a separate JavaScript file. So for the examples I'll give you, and I'll give you my website where we have lots and lots of examples of this, you'll see a pair of files for every application. The HTML file that'll have the shaders and everything to get going, and a JavaScript file that'll be, for those of you who've programmed OpenGL, will be a little more familiar. You'll see things that look like all the familiar OpenGL functions in it. Okay, so here's my really trivial, as simple example as I can give you, which is to do just generate one triangle. All of the code that you're going to see, and I'll show you some of these code examples later, they're all on my website. The website you can get in various places. It's in the notes. If you just if you just do a Google search on me, you'll come up with this. It's in the book, every place else. So let's look at this. So the first thing we're going to do is look at the HTML file. So here's a really trivial HTML file. What does it do? It says, okay, here's an HTML file. You see the tag at the top. We can divide it up into a head and a body. That's not even necessary. But we now want to stick in the vertex shader and the fragment shader. What we're going to do is give each one of those an ID so that we can refer to them in the application file, in the JavaScript file. So the ID is my name that I'm going to refer to at vertex shader. But the WebGL and HTML understand the type. They understand that if I say what's coming next is X shader, X vertex, it says what follows is a vertex shader written in the GLSL language, and and what follows now is the shader. It's an absolutely trivial what's called pass-through shader. It simply takes in something called vPosition. That's what I'm going to produce in my application code, and all it does is output it as a position. So it's simple in the sense I'm writing it in a coordinate system that is the standard default coordinate system, that everything that's inside a box that goes from X, Y, and Z from -1 to 1 in all three of them is going to fit in the clipping window, and so I don't have to worry about scaling anything. We'll do that later. So all I'm going to do is pass through the position. The position comes in as an attribute of type vec4. So what we're going to see when Dave talks about GLSL is a very C-like language, but it has some basic atomic types which fit in very well with graphics. Namely, it has 2, 3, and 4-dimensional vectors and 2, 3, and 4-dimensional matrices, which are basic types in the language. So we're saying we're going to input a position, and we're just going to send it out through what's called a built-in variable GL underscore position, which is known to the system, so I don't have to declare it. So that's the end of my vertex shader, and then I'm going to have an equally simple fragment shader, which says just color every fragment that you're going to output, color it red. So it's going to be, I have a constructor that constructs a vec4, which is red is fully on, so it's green is off, blue is off, and the final one is, as usual, the alpha value that says it's opaque, again through a built-in variable GL frag color. Now, one note for those of you who have done shader-based programming before, in WebGL, at least in this version that we're version 1, you have to specify the precision. This was an issue that comes from OpenGL ES, which had to support low-power devices and devices that might not have a lot of precision in their displays. You're guaranteed to always have support for medium precision, but for reasons that maybe Dave can explain, it doesn't simply default to medium precision. You must have a precision statement if you're running WebGL 1. So medium precision will always work for floats in there. Okay, so now we can say what else do we need to make this all work? Well, I need some other files too. There's a set of utilities, WebGL utilities. I believe these come from Google. They're standard. They're there to help you set up the WebGL context. We've created a couple of programs to help you, one of which is an init shaders program. There's a lot of steps that go into initializing your shader. We'll go over those in a little bit. They don't add a whole lot of understanding of the graphics side. They're just things you have to do. You have to read the shader. You have to make sure you read it in okay. You have to compile each shader, make sure that completed. You have to then link the shaders together to form what's called a program object. So we've hidden all of that stuff in a function that we have on the web called init shaders, and we'll go over that shortly and to say what's in there. And finally, we say, well, read in your application. And our application for this simple program is going to be called triangle.js, which I'll go through in a second. And finally, in the HTML file, we open up a canvas. So we give it a height and a width. We give it an ID. Again, we're giving it an ID so we can refer to it in the JavaScript file. And if it doesn't work, you'll get a message saying your browser doesn't support the HTML5 canvas element. But virtually every modern browser will now do it. So that's pretty standard. As you go from program to program, you'll see essentially every line in there is the same. You're just going to change the application and put in more complex shaders. Now, what goes inside of the JavaScript file? Well, what we have to do is now set up what's called the OpenGL context. So we gave the canvas an ID, GL canvas. We now get that element. So get element by ID is a JavaScript function that will get that from the HTML file, and it will set up what's called a GL context. The context, basically, it's the canvas and all of the WebGL functions. So basically, it's saying bring in OpenGL, but WebGL in this case. And that object has all of the constants and all of the functions that those of you who have done OpenGL are familiar with. So basically, it's a one-line initialization. Okay, so now let's do our triangle. And now everything should be very, very simple. So, okay, so let's get the vertices of the triangle. So what I'm going to do is set up 3 vertices at -1, -1, 0, 1, and 1, -1 as the 3 vertices. Now, here's one thing. This is a JavaScript thing that's one of sort of the gotchas that you're going to have to worry about, is everything in JavaScript, with almost no exceptions, except for numbers and strings and Booleans, everything else is an object. And as an object, it has methods and it has attributes. So when you think you're setting up a simple array in JavaScript, you're not. You're declaring an object that's not what OpenGL is going to expect on its end. Now, one way to get around that, we're going to give you a second way in the next example, is to use what's called a typed array in JavaScript. So in typed arrays are a JavaScript object, but in fact it's a JavaScript object that acts like a C-like array. So if you want something that acts like a C-like array and probably executes faster, you can just set up an array as a new float 32. If you want an array of bytes, there's a uint8 array that we use in WebGL a lot. So that's one way to go, and I'm doing it in this example. So there's your data. And now we do sort of our standard kind of stuff. We set up a viewport, which is the whole thing. The canvas was the HTML5 canvas we set up with a width and a height. We can clear it to be, it's in this case, white. We now have to now worry about setting up the shaders. We do that. We said we're going to give you this program, init shaders, which just takes the ID of the 2 shaders that we assigned in the HTML file, the WebGL context, and then sets up a program object. You can think of a program object as being a container object. It's something that includes all of your shaders. You may have more than just the 2 shaders. You may have a bunch of auxiliary functions that you wrote in GLSL. All of those can go into a program object. And so we set up, in our case, we'll just use a single program object. We say use that program. So one of the things you can do is switch between program objects at will. If you set up a bunch of program objects, you can go back and forth with them with just the use program function. Okay, now let's get the data to the GPU. Okay, so I create a buffer on the GPU. I bind that as the present buffer that I'm talking about, and I now send those vertices over. So there's 3 functions. There's set up the buffer, create buffer. There's bind that buffer, make it the present buffer, and buffer data to send those vertices out to that buffer. And now our data is on the GPU. So all of this stuff was set up. It's going to be the same in pretty much every program. Now the rendering itself should be pretty straightforward. One more step I have to do, which is say, well, how do you now line up the functions that you have in the shader with the functions that are in your application? Well, when the linking everything together happened, tables were set up, and so I can now get where the position location is using a function called getAttributeLocation for the name in the shader. I used vPosition in the shader. I get that name. I say what form is the data. It's two-dimensional data. It's floats, a couple of other parameters. The data are not interleaved. And then I enable that array that I set up. Now rendering is just simple. I just clear and I draw the arrays. That's it. So for one triangle, you could say, well, that was a lot of stuff. But all of that stuff, if I had a million triangles, would be essentially the same. I do it once and I do it in other programs. So let's look at another example. Let me talk a few minutes about sort of what primitives and what options do you have. I think most of you know that in computer graphics, everything is stored in four-dimensional, what are called homogeneous coordinates. So whether you specify things in 2 dimensions or 3 dimensions, they're always going to be stored as in four-dimensional variables on the GPU. So a point will have x, y, z, w values. If you store a color, it'll be stored in 4 dimensions too. Now the data is stored in vertex buffer objects on the GPU. Now what options do you have for what you can actually render those data as? And it's very limited. It's more limited than in the original OpenGLs. We can render points. So when we have GL draw arrays, we said GL triangles and we drew one triangle. You can do triangles, you can do triangle strips. In a triangle strip, every time the first 3 vertices define the first triangle, each additional vertex is connected back to the previous 2 to get a new triangle. So you're going in the limit to 1 triangle per vertex. A triangle fan is similar, except that you always have the first point is fixed, and each new point after the first 3 is connected to the previous point and that initial point. These are the filled primitives. If you want lines, GL lines will take each pair of vertices and connect them. GL line strip will connect all vertices but not the last back to the first. And GL line loop will close it by connecting the last vertex back to the first one. And you also have GL points to just display things as 1 or more pixels for each vertex position. Okay. So now let's look at a little bit more complex program that'll sort of introduce some of the ideas of modeling and a little more about how you can initialize more vertex data. Now, there's generally, when we talk about geometry and we say, what is a vertex? You say, oh, a vertex is just a position in space. In OpenGL and WebGL especially, as we've gone to shader-based, a vertex is really a collection of attributes. So a vertex has an attribute which is its position, and generally, almost every application you will do, every vertex will have x, y, z, or x, y, w coordinates, but it'll have other attributes. For example, its color. If you're doing shading, a vertex might have a normal attribute. If you're doing texture mapping, a vertex will have texture coordinate attributes. So in terms of what you'll see in the code, these are all just attributes that are associated with a vertex, and we can send any set. And if you can make up your own, and that's another thing that we're very flexible about. If you have an application where you have a temperature associated with every point in your geometry, you can just assign temperature as an attribute and have that go through the system. Okay, so we'll see how we do that, and then we'll get to talking later about how we can do a lot of this interactively and animate what we're doing. So let's take this example of a cube. So okay, so what is a cube? Well, depends how you want to look at it, but a very simple way to look at it is say a cube is something that has 6. Well, we can start off and say, well, if I want to have a cube, I have 8 vertices. It has 6 faces and it has 8 vertices, and I can define it by its faces, I can define it by its vertices. But you could also take the attitude that says, well, look, WebGL only knows how to display triangles. It doesn't even know how to display quadrilaterals. I mean, those of us who have been doing OpenGL for a long time, well, we're used to having quadrilaterals at least. That isn't there. So every triangle or every quadrilateral is two triangles. So you can either display it as two triangles, you can display it as a triangle fan or as a triangle strip if you want, but it's two triangles. So here would be a very simple way to say, if I'm going to display this cube as just triangles, there's now two triangles per face. There's 6 faces, so I have 12 triangles. Each of those 12 triangles has 3 vertices to define it, so I have 36 vertices. Not the most efficient way to do it, but brute force, that's how we can do it. Next thing is that we have decided if we're going to communicate with GLSL, what Dave and I decided when we were going through this new edition of our book was to say, well, you would like your code in your application to look something like the code that's in your shaders. And the shaders have these types, mat2, mat3, vec2, vec3, vec4. Those aren't types in JavaScript. So what we did is we added a library, and again, all of this is on the web, where we added types ourselves in this library we call MV for matrix vector .js, which mimics the types that are in the shading language. And there's 2 or 3 advantages to this. One of which is that I think code-wise, I think it's easier to see what you're doing, but also as you start studying, what's the best way to do something? Do I do this in my application? Do I do this in the shader? It turns out that the code, if you use the same types, looks the same. And you can move code from a vertex shader to a fragment shader, or especially when you're doing things like transformations, which will be one of our examples. When you're doing a transformation, do I do that transformation before I send the data out to the GPU, or do I do it in the GPU? Well, the code will be almost identical, and it'll be easy for us to then move code back and forth and find what's the most efficient way to do a given application. So we really like using this package. It also has a bunch of the viewing functions that those of you who use the fixed function pipeline may miss. We put those in there for you. Okay, so let's do this. So what I'm going to do is I'm going to display a cube with 2 attributes, okay? It'll have a position for each vertex, and each vertex will have a color. And what I'm going to do is create 2 arrays to hold those vertex buffer objects. Now, I could do it a lot of other ways. I could put it all in a single vertex buffer object. I can interleave colors with positions, but I'm going to do it as 2 separate ones in this example. But all the other forms are certainly possible. So here we go. So here's using our types. This is in the JavaScript side. So here's a little cube. I've numbered the vertices 0 to 7, and I'm going to define an array. So it's a JavaScript array. So anything between the braces is a JavaScript array. It's an object, but within that object, it's an array of vec4 types, which are the types that are in our MV.js package, and they look pretty obvious. They look like constructors that are constructing 4-dimensional vertices inside of that default cube. Okay, now for the colors, just to show you the difference, the colors I could have done exactly the same way. Here I've done the colors as a JavaScript array of JavaScript arrays. So that's an array of arrays to get the 8 colors that I'm going to use to color my cube. Do it either way. Okay, now here's where the problem occurs in both cases. We said that a JavaScript array is not a C-like array. And when you're sending the data over to the GPU, it expects to see it in a very, very simple form, as it expects a C-type of array. So we have a function in our library that does exactly that. It's called flatten, and it will take out just the data it needs, form it into a simple array, and send that over. So when you send the buffer data over, if you look here, over here, this flatten function will do exactly what you need done. It'll take the JavaScript array or whatever JavaScript type, strip out the data, returning just a string of the data or just the values, and send that on, and it'll be exactly what WebGL expects to see in the shaders. So that'll take care of those kinds of issues, which at first can be kind of ugly. Okay. So here we go. So we can generate our cube by having a quad function that just takes the data and puts it into an array. Now here's another issue with JavaScript that's actually very nice. You can get rid of a lot of indexing because JavaScript arrays are objects. They have methods, and the JavaScript array has push and pop methods. So rather than trying to index everything, we can just do push, 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 push to create that array, which is a lot cleaner code, a lot more efficient code, and that's very, very nice. So we form the two arrays. Now I can form 4 quads with that, or excuse me, 6 quads with that little function, which are actually 2 triangles per quad. Now I do exactly as I did before. I create the buffers. I bind the buffer to be the present buffer. I send the data out, the point data, and separately do exactly the same thing for the color data, which should somehow be in here. Yes, I do exactly the same thing with the color data. I then link things together, saying, well, I call in the shader, I call it vColor, and call it vPosition. So I now use the vertex attribute pointer to say to line up the names in the JavaScript code with the names in the shader code, and I do that for both the positions and the colors. And finally, I'm ready to render. And when I render, it's just draw the arrays, draw those 36 vertices that I created and I pushed into those arrays, and just run. Now, the request animation frame I'll come back to. That's the recursive part where if you want to keep, for example, this example is simple. You just draw once and you're done. If I want to keep changing things, the example will give you a little bit, is I want to rotate the cube. I have to render it again and render it again. So the easy way to do it is to use the JavaScript function, request animation frame, and what that'll do is just recursively call itself and re-render. This here example, as I said, it doesn't really matter because you're not changing anything in here. And we'll come back and discuss animation a little bit later. Hidden surface removal is very much like, if you're familiar with OpenGL, you have a depth buffer, it's in there, you just have to enable that depth buffer. You clear the depth buffer just like you clear the frame buffer. So that part is exactly what you're familiar with. So let me turn over to Dave to talk some about GLSL and the shaders now.
Check for questions, or? Okay. Keep questions to the end. Right. So it turns out in this whole mechanism, shaders are crucial. Ed talked to the part where you put your data into the system and initiate the drawing, as you just saw, which launches all the processes that occur on the GPU. And you define what those processes are by writing 2 kinds of shaders. The first type is what's called a vertex shader. Now, when Ed described the cube, right, those points that we formed that we used in the quad method to make it all together are vertices. And each one of those will be processed by a vertex shader. I'll show you one in just a moment. It's a little program that you write in a special language called GLSL, the OpenGL Shading Language. Specifically, it's OpenGL, or GLSL ES, the embedded subsystem version, commonly called ESSL if you happen to look out there. There are too many letters flying around there, and I'm too dyslexic to get them all straight, but you get the point. The way this works is vertex shaders are the thing that take your raw data, the objects that you've defined with your vertices, and transforms each vertex independently. So, for example, you have a cube. OpenGL doesn't see a cube, and nor does WebGL in this case. All it sees are 8 vertices, and you can move them around any way you want. The fact that you said, oh, let's draw this as 2 triangles was what effectively connects the dots and associates them together. So that's something to keep in mind when you're writing your vertex shaders. You have a very limited set of data you're working with. It's the current vertex and any of those attributes, which we'll describe more, that come along with it. You can't look to see which neighbor you're connected to or some other parts. The big OpenGL pipeline that you find on PCs and other types of machines does have a shading stage that does something like that. And that's not a vertex shader, it's called a geometry shader. But WebGL is sticking down to the simplest pieces. So Vertex shaders, though, do a tremendous amount of work. You can't really, I should not diminish the value of them. They're what take, an object like, let's say you wanted to draw this room. Now, one way you could do it is model each chair in its spot by figuring out, like, okay, this chair is 15 feet from the wall, and then figure out what it looks like. And then I do the same process for the next chair because it's 11 and a half feet from the wall. But, all these chairs are kind of the same. So you could model one chair on a convenient coordinate system, going like, oh, let's put the origin right in the middle of the seat and figure out what the size of the back is and the legs. And then let's figure out how to move that chair all around. Well, that moving the chair around is the operation that you do in the vertex shader. So that's really a common thing, and we like those changing coordinate systems. We have a slide coming up in a little bit when we talk about transformations to show there's a rich plethora of coordinate systems you get to play with inside of WebGL. It turns out, you get to control this entire pipeline, so you need to understand a little bit of the mathematics behind computer graphics, but there's nothing too challenging. Moving vertices, well, that's just, once again, updating coordinate systems, and computing per vertex attributes. In this case, it mentions lighting, or perhaps you use some of the physical values that Ed talked about to actually convert those into something. So let's say you're doing a visualization of temperature, and you've recorded the temperature at each point on some surface. That point in the surface would be a vertex. The temperature would be a parameter that you pass into a vertex shader, and then you can use that to color the surface or to modify the position as it goes on. There's tons of things you can do in these things. It's only limited by your imagination. But the mechanics, quite a bit to it. Now, the other side of it are fragment shaders. The way the pipeline works is geometry is kind of set up in the world that we live in. You think about 3D objects, the points that describe them, and how they fit together. Ed mentioned the rasterizer. The rasterizer basically is the thing that takes those 3D objects and figures out which dots on the screen they're actually going to light up. Each one of those dots is processed separately by a different shader. Vertex shaders run once per vertex, and you have a pretty good idea of how many vertex shaders are going to run, right? You said to draw the cube, we draw 36 vertices. Your vertex shader will be fired 36 times. Fragment shaders, on the other hand, are fired off by the rasterizer. And so the number of fragments that are actually generated from a single triangle depends on how much screen area it covers over top of that. So you could wind up drawing a single fragment if your triangle shrinks down to a pixel, or you could basically fill every pixel on the screen by making your triangle very large, right? And a fragment shader will be run for every pixel that's visible on the screen, so you don't have to worry about the edges that poke out. Your fragment shaders are the ones that are responsible. They have a very simple job. They just compute the color that is associated with the pixel on the screen that's going to be lit up. But that doesn't mean that pixel is going to take care or actually get that color, because there's some pieces that we'll talk a little bit later about called pixel tests. And one of them, for example, Ed just mentioned the depth buffer. Maybe that pixel comes from an object that's behind something else, so you really can't see it, so that's discarded. We still generate the pixel, your fragment shader is still executed, but the results of it might not contribute to the picture. And that turns out to be an optimization point. Inside of fragment shaders, you have a whole lot of different options for computing the color. Some is just straight, direct, simple color computation, like you saw in the previous example that Ed showed you, right? They set the color of the triangle to just red. That's the simplest fragment shader. But you can get many more complex things. We'll talk about a technique called texture mapping, where you look the color up in a picture. So you take an image and give it to the WebGL, and you say, for this particular point, tell me what color's there, and then I'm going to use that to actually compute the color. All of that happens inside of your fragment shader, and we'll talk a lot more about the capabilities that are in there. But at the fundamental level, it's really quite simple to write a vertex shader and a fragment shader. As things start to get a little more complicated, your shaders get a little more involved, and you move on from there. The good news is, both types of shaders are written in exactly the same shading language. So if you're comfortable programming C, or you're feeling comfortable programming C++, if you've got C++, GLSL is a piece of cake. If you've got C, there's only a few additional rules that you need to be aware of. They use something called constructors. You just can't shove values into places. You have to make a little function call to do it. That's the most complex piece. So it really is, it's a very C-like language. There's the same semantics of declaring variables, using braces, any of those kind of pieces. But it also has a lot of types that you'll find very useful in doing computer graphics. Computer graphics is kind of the visual manifestation of math. It's the reason I went into it, right? And, how many of you took linear algebra in high school? When am I ever going to care about this matrix stuff? Guess what? Your day has arrived. Computer graphics is entirely based on three-dimensional graphics, I should say. It's entirely based on 4x4 matrices, because 3 dimensions just doesn't do you justice. Well, it turns out GLSL has very convenient types for working with these kind of matrices and doing the right operations built right into the language. In one line, you can do a matrix multiplication. No more of this triple for loop and any other garbage. You just get it done. So we'll talk about those in just a second. There's a whole lot of additional features that are inside of there. There's a richer set of functions I'll talk through and some of the other features. So like any program, every shader begins with main. And so as we show you the examples and the examples you just saw, there is a main function. It's void. It doesn't return a value like if you're writing a C program. Just void main, and bang, off your shader goes. Shaders also use a lot of global variables. For those of you who are purists in your programming, sorry, it doesn't work like that. Our global variables are special. That's how the WebGL passes data into your shader through a bunch of variables that sit outside of the main function. The same thing happens for your fragment shader. The vertex shader passes them through there. It's not like you're passing parameters from one to the other. So your main never takes any parameters. But we'll explain exactly what the global variables are and how it works. Now, certainly you can do lots of locals, but things that come in from your application, like you just saw Ed set up, are going to be globals. Now, first place to start with any programming language are the data types that are there. And sure, we got floats and we got ints. But we also have vectors of those things. You combine those together, and they work as a singular unit. So quite often, vertices will be described as a vec4. Now, that 4 comes in from the fact that all the matrices want to be 4, but we'll explain a little more in transformations why it is, but hang on to this thought. This vec4 is something called a homogeneous coordinate. The x, y, and z is exactly the x, y, and z that you'd see in a three-dimensional space. And then because we didn't have a letter after z, we ran back and picked up w and stuck it to the end. W is this thing that makes it a homogeneous coordinate. It makes all the mathematics so much simpler. That's why I can say everything's done with a 4x4 matrix. W is usually 1, and if you change it around a little bit, it turns into a scaling factor. Just squirrel that away. You probably never have to use it. But we have features for doing those kind of things. So we'll see in all of our examples, vertices come in as a vec4, and the last component will be a 1, and x, y, and z will be the appropriate values in between. We have two-dimensional vectors. We'll use that quite a bit for two-dimensional problems, whether you're we'll use it a lot in texture mapping because that's looking things up in a two-dimensional table, or maybe to make your programs run a little more optimal. Let's say you're just doing some kind of map that is just in 2 dimensions. Z is always going to be 0, W is always going to be 1. You can cut the bandwidth down to the GPU by using a vec2. Now, to be truthful, it turns out most GPUs will actually take and unpack your vec2 data and make it vec4 because they optimize the hardware for that particular case. So you want to make your programs run fast, do a little couple of tests inside of there. Your mileage is going to vary across platforms. For the vector types, we have floating points are just the undecorated versions, so vec2, vec3, vec4. If you stick an I on the front, they become integer vectors. And if you stick a B on the front, they become Boolean vectors. So within WebGL 1.0, and actually I guess 1.1, those are the only types that are available. 2.0 is being designed and coming out. Desktop OpenGL has a much richer set. You can have unsigned ints and long variables and all the kind of common data types because that version of the shading language is heading off towards doing what's called compute shaders, running generic computation on your GPU. WebGL still concentrating on, hey, do your graphics on the GPU, do your computation on the CPU. So they're still pretty simple. We also have our matrix types, MAT 2, 3, and 4. Those are 2, 3, and 4 dimensional square matrices. They don't have in WebGL like 2 by 3 matrices or any of the permutations of that. They're all just square. And they're all floating point. Now, there's some interesting things you can do with that stuff, but you'll find that that will take care of most of your needs. When we talk about texture mapping a little later on, we'll talk about these special variables called samplers. A sampler is nothing more than a handle to a texture, and a texture is nothing more than a special image that you give to the GL that you can do stuff with. When we talk about that, you'll see that as our declared type, and you can kind of see they represent different use cases. One-dimensional, two-dimensional, and three-dimensional textures are stacks of images, whether they're just a single row of pixels, a square of pixels, or a cube of pixels, that you can look things up in. Cubes are special cube maps. They're a little more advanced than we discussed in this class, but they're done for using environment maps. So you store a 6-sided texture map in there, and it makes your objects in your scene look reflective. Sorry, we don't have time to discuss the examples, but there's ample literature out there for you to be able to look that up. Now, I mentioned this point before. The C++ part that's creeped in here, you can, when folks talk about C++, you've got new and you've got delete and you've got iterators and you've got templates and all this stuff. No, none of that's in here. The only thing we borrowed from C++ when designing the language was the concept of a constructor. And you can see here in our example that we use a constructor the type that you're going to declare the variable into, you just put the parameters and do this, and this makes the compiler happy. We know what's going on. Now we'll see that we can use these types and constructors to make more larger types. So for example, if this were a vec4, you could do a vec3 of something and some other value over here and put parentheses around it, but you'd still need to construct that variable. There's no way to just do vec4a and add some extra bits into it. So as you initialize any variables, you're always going to have to construct them. After that, you can just add the pieces together. We'll show you some of the interesting things that are available in GLSL coming up here in just a moment. But those are the fundamentals. If you can grasp that, you can get your shaders going very quickly. Now, because these are types, right, you don't have to worry about doing the fundamentals. You know, if you're writing C and you don't have C++ where you've defined some kind of matrix class, you want to do a matrix multiply, you're writing 3 for loops, right? Your code gets big and huge to do nothing. In this case, all the operators are defined in what makes sense in a common sense way for all the different types. A mat4 has a multiplication operator, and it knows, hey, if you give me a vector, I'll check and see that the dimensions work. If they don't, math isn't legal, I'm going to toss an error for you. And that happens in compile time. I'll tell you a little bit more. Runtime errors don't happen in GLSL. You'll always get something out the other side, but what you'll get is not what you're expecting to see, but you'll get a value that kind of works. Compile time helps you out with a lot of stuff. So in this case, we can modify our matrix M by any of those 4 vectors A, B, and C and do the right job. Now, here's an important thing. Inside of computer graphics, your vertex or your vector, you always want to be the rightmost thing. It wants to be cuddling up with the semicolon at the end of the line. Because the way we'll teach you how to do transformations will accumulate the different types of coordinate systems together using just basic matrix multiplies. Each coordinate change is represented by a matrix. We can stack those together by just multiplying them in. The thing is, the way we do this is you start on the left and start adding transformations that direction, but you always put your vertex on the far right, next to the semicolon. It's perfectly legal to do that on the other side, but it completely changes the math. And all of a sudden, things that used to be unseen, if you reverse that, will go disappearing off into space. And you go, I used to have graphics in that window. What have I done wrong? Debugging these things is a little difficult. There aren't a whole lot of good debuggers for debugging OpenGL. AMD has a product that I remember does that. I'm not sure if it actually works with WebGL. There's a lot of trial and error because this is happening on some device deeply embedded inside of your system. So the right answer, and this is really important, is use, if A is your vertex in this case, use the C version here, and this will transform A by the matrix M. This is perfectly valid, and it multiplies your vector times a matrix, but it's going to do the wrong thing, or quite likely not what you want. So that's the words of wisdom you need there. Now, each one of these vectors and matrices, for that fact, allow you to use what are called accessors. They're also commonly called swizzlers. And this is because, you know, you could do normal vector indexing of these data types using square brackets. So, you know, the first element is square bracket 0, second element is square bracket 1, normal C-based things. But when we think about it in computer graphics, right, well, if this is a vertex, the values that are inside are the X, Y, and Z coordinates of what I'm looking at. You know, and if I'm working with colors, well, colors are RGB. Yeah, I could do 0 and 1, but it's a lot more expressive in your shader to use things that make sense. So, as an example for the vectors, you can use what's called a swizzler and append an XYZW after a little dot. So you have a variable type here, a dot, and then some combination of these things that allow you to access the various elements inside of your vertex, or inside of your vector. Same thing for a matrix. You can do, you know, matrix M square bracket 0 dot XYZ, and that will return the first 3 elements of the first column. Now, why is that handy? Well, it lets you first make your shaders work a lot simpler, and it allows you to do various operations much more easily. So, as one example, here is the same way to access the second component of this vector v, just to be complete in this part. Now, that's useful, right? So if I'm working with geometry, I might use the y. If I'm working with color, I might use the g. And if I'm working with texture maps, which I'll talk about in a moment, I'll use the t. Now, you'll note everything, look, this is not correct. So XYZW, perfectly fine, makes perfect sense. RGBA works really great. For texture coordinates, this should be STPQ. He gets a timeout. Sorry about that on the error. Right, we've already used R over here, so this is a P. It turns out for texture maps, most of the time your applications are two-dimensional and you use just S and T. Now, this allows you to do that, to more simply access these things. But the real magic comes in when you start combining them together, as we demonstrate down here in the bottom of the screen. So this is a very simple example, but it shows some of the power of it. This allows you to take the first two elements of the vector B, reverse their order, and assign it into the first two elements of vector A if both of these are vec4. Now, you'll see us using that kind of technique quite often when we get to texture mapping, or, let's say, for example, you want to do a monochrome image. You can just strip off your Rs or take your RGBs and multiply them by the appropriate weighting factors and just write them back out. And the swizzling notation is what it's called, with the dot and the variables after it, works any way you want. So if you want to take and populate a vector with the first value, you can do .xxxxx, and that will populate x across all four things. Any valid combination of letters of the same group is perfectly valid. So you can do xzyw and take and shift the z component into the second position. Works perfectly fine, compiler's certainly happy, but you can't do like xyst, because then you're kind of crossing the beams, bad things happen. This is a really powerful feature. As you start to get more familiar with it, you're like, oh, look at these cute things I can do. The other nice thing about these are each one of these usually equates down to about a single instruction inside of a GPU, which makes them very fast operations. So, the instruction sets I've worked with are extremely large at the hardware level because they're masked behind, I just took these letters and moved them around and it does different things inside of the pipe. Now, this is the important part where this does what I like to call plumbing. Ed showed you how to take data from inside of your application and get it down to the shader. Like, okay, we take and declare all our vertices, and then we put them into a buffer using buffer data call, and then we draw the data that's in that buffer by calling something like draw arrays. Ed demonstrated that just a bit. Sorry about that. That's great, but how do I take this stuff that's written in my JavaScript application over here and get it into the shader that's running God knows where inside of the system? Well, the way you do that is by decorating variables inside of your shaders. I thought I had frogs for lunch, but maybe I was wrong. So inside of a vertex shader, data that you put into a buffer is called an attribute. So let's try that, shall we? The position is an attribute of a vertex. Good thing they can edit that out in the film. So attributes describe things about a vertex. A vertex is not a position. Position is an attribute of a vertex. When you think about a vertex, think about a small bundle of data, right? You've got a point in space, and maybe it's got some colors that go with it. Or maybe it's the temperature and barometric pressure at this point in space. It doesn't matter. WebGL doesn't care what attribute you attach to a vertex. All it's going to do is make sure all of those get shoved down into your vertex shaders that you get to go off and have a lot of fun with. So anything tagged as an attribute is a value that's going to be read during a draw call in one of those buffers you set up way over there. And we'll show you how this plumbing all fits together in just a little bit. So inside of your shader, you'll go attribute, vec4 position. And as you saw in the previous slides, in our shaders, we try to be consistent and call the position vPosition or vPos. So we'll always label that as an attribute, and that means the data is coming in from the application. Now, remember, your vertices are processed. They're stuck into the rasterizer, which then takes and assembles them into a geometric primitive, figures out which dots across the screen they light up, and fires off a fragment shader for those. There needs to be some communication between the vertex shader, like, well, I took this vertex that came into me from the application, I've transformed it, so here's its new screen location. Well, that's really important for the fragment shader to understand where it's going to go. So we need some way to get the data between the vertex shader and the fragment shader. Those are what are called varyings. And they're called varyings because across a primitive, so if you take a triangle and rasterize it, the values will be interpolated across the three vertices and all the attributes that go along with it. So each attribute's value will be interpolated across all the different fragments that compose that polygon. Now that's really useful, and that's where the name comes from. So varyings are varying data, and varyings appear both in the vertex shader and the fragment shader because that's basically two ends of a pipe. You put some data into the varying variable in your vertex shader, and it will magically appear in your fragment shader, but it'll be updated to represent the values that are needed for the pixel you're currently processing. So we've shown you a couple of flat things, but as we get into more examples, as Ed shows you some more later, we'll see how the colors change across a primitive. Those are all varying values. The color will be varying because it changes across the primitive. Well, if something changes, odds are something can stay the same. And this is a value that's called a uniform. And a uniform basically says the uniform, or the value of this thing is uniform across the primitive. Now, the reason you have uniforms are they're like allow your application to send constants into the shader, but you don't have to attach them as attribute values because that would kind of waste bandwidth. So this is a nice simple way to do that. Uniforms exist both in vertex shaders and fragment shaders. And really, from the view of the shader, if you imagine yourself inside that little application, a uniform is just a constant value. It doesn't change, and the compiler can do whatever optimizations it wants. It just knows there are values coming in. It can combine them, cache them, do hoisting and all other sorts of stuff. In some of ours, some common examples, like where would you use this? Well, you might put a floating point value as the time and use that in an animation. I query the time, and I'll use that to update what kind of things are. With respect to the shader, any vertex is going to be processed at the same point in time, so that's a uniform value that goes across it. You might do a rotation vector. All the objects in your scene, or all the vertices in your object, want to undergo the same rotation. So maybe we code that into something. That's a uniform. So we see uniforms coming in a number of different places to pass data from the application down to the shader to use for useful stuff. Just a quick note about functions. It's a programming library. There's a standard library of mathematical things. So unfortunately, there is no printf inside of this. So when we talk about functions, you don't even have the basic rock to bang together to do debugging like most of us drop to when we have to write code. Doing shaders, your best trick in debugging them is starting simple, setting it to a color that you understand, and starting to work on that part. Once you establish the position of something, get it on the screen with the right color, then start messing with the color part. If you try to do both simultaneously, it'll just be a disaster. Yeah, they shouldn't leave me out in public. But we have lots of math functions. We have a lot of trigonometric functions, so you can do sines, cosines, tangents, arctangents, all that stuff. A lot of different things for operating on vectors. You can compute the length of a vector. You can normalize a vector. You can reflect a vector around another vector, which turns out to be kind of useful for lighting. Lots of good stuff. Well, that's all the goodies that go inside of there. There are a couple of things we need to take care of, because GL, and in particular WebGL, based on OpenGL ES, defines some variables that fill in a bit more of the plumbing. So for example, your vertex shader has the responsibility of updating the position, right? Because the position is going to be used by the rasterizer to figure out which dot in the screen to start drawing on. Well, inside of GLSL, there are 4 built-in variables that we find pretty interesting. I think there are a couple more, but these are the ones you use most often. And the most important is this one called GL position. This comes out of the vertex shader. This slide kind of glomps with vertex and fragment shaders together. You must write GL position. That is, GL position must appear on the left-hand side of an equal sign somewhere and have a valid statement that assigns 4 values into it. Now, that guy is basically the transform vertex position coming out of the vertex shader. It goes into the rasterizer, and the rasterizer uses that information to figure out which fragments inside the window to light up. Inside of a fragment shader, there's a variable called GL frag color, and that's the color that you want to set the pixel to. Now, both of these statements usually will appear pretty kind of like at the end of all your shaders, because you're going to do a bunch of computation and use that to figure out the position, or a bunch of computation and use that to figure out the color of a fragment. Now, there are a couple of other things that come into the shader. One is called GL frag coord, and that's basically what is the XY pixel on the window. Well, specifically, that's the XY pixel inside of the viewport. Am I working with? So if you want to do image processing operations, you can kind of write your shader assuming you can figure out which pixel you're looking at and then do some operations along with it. Just like I emphasized with vertex shaders, you only get data dealing with a single vertex. Same thing for a fragment shader. You only get information about the fragment you're working on. So you can't go, oh, what's the fragment? If I take and decrement X here, do I get the fragment next to me? Nah, it doesn't work that way. But we'll talk about texture mapping, and it'll show a really great example of using an advanced concept called frame buffer objects. We won't talk about them in depth, but this allows you to basically take a picture of the frame buffer and then be able to do those kind of image processing operations quite simply. Frag depth is kind of the same thing, but for the depth buffer. You can kind of poke the depth buffer and see what the computed depth value of your fragment is and use that for various computations. So these 2 guys, GL position, GL frag color, must appear in the respective shaders. The other is around for some diagnostic stuff. So let's put all this together and look at an example. So this is the vertex shader for the cube object. So hopefully from what you heard, and if you can put those things together, we're going to put 2 bits of data into the vertex shader. Those are our attributes. One is the position, and the other is color. And just because you kind of want to be consistent about this stuff, we call it vPosition, vColor, and you can see those guys up there. Now, we need to take some data from the vertex shader and pass it down to the fragment shader. And so that's where we declare our varying variable, and we call this fColor to remind ourselves that this is going to the fragment shader. And here's a real simple shader. It just takes and transfers the vertex color down to the fragment shader. We'll see that coming back. And just sets the vertex position to be the position in the screen. Now, this shader's kind of uninteresting, but dimes to dollars, when you can't figure out what's going on with the geometry, you'll wind up writing something just about this simple. This draws in something called normalized device coordinates. So if you want to go out and play with WebGL today, and you're like, I got to brush up on my math, I don't understand all these transformations. If you open a canvas, you'll get a window that basically goes from -1 to 1 in both the x and y directions. If your vertex position falls between -1 and 1, it's going to wind up on the screen. So this is a great way to start working with two-dimensional graphics to get your feet wet inside of this, and this shader is going to be really handy. So that's a great starting point. Now, that'll take care of processing all of our vertices, and you see GL position, which is a declared vec4, is assigned to takes its value from another vec4. If this were a vec3, you get a compiler error. So you just have to be consistent on types and be able to write all the right things. Well, how about the fragment shader? In this case, it actually gets a whole lot easier. First, as Ed pointed out and asked me to comment on what is this precision medium P, remember the lineage of WebGL comes from working on cell phones, right? You got these things. When cell phones first came out, memory was precious. So a floating point number, if I were to ask any of you who are programmers in the audience, the size of a float is normally 4, right? It's 4 bytes, 32 bits. Well, 32 bits is expensive, and it turns out for color, when you're rasterizing down to, say, 16 colors a pixel, 32 bits is a bit of overkill. So when they first started making OpenGL ES, they gave the option of taking floating point values and giving them variable sizes of bits. Now, there's a medium P, unless you're shopping at Starbucks, where it would be, what, tall P and grande P or vente P. We have a low P, a medium P, and a high P. Low P is 8 bits for a floating point value, medium P is 16 bits, and high P is at least 24, maybe 32. So the spec doesn't force a 32-bit because, right, memory inside cell phones is expensive. It takes a lot of power and other things. So that's why they did this piece. As Ed mentioned, if you put medium P, it'll work perfectly fine because most of the frame buffers are only doing 8 bits per component, so you get plenty of precision inside of there. If you do high P, it may make things go slower, so we just recommend sticking with that. Now, because this value is coming from somewhere else, it's a varying, and the compiler, which I'll talk about in just a moment, matches your varyings in the vertex shader and your varyings in the fragment shader. It doesn't care if they don't match exactly. What it cares about is if you're using one of these in the fragment shader, there better be a value that matches it in the vertex shader. So this guy could have 10 other varyings and not actually use any of them inside of here, and that would be perfectly fine. What it will flag you on is saying, hey, you didn't write this value over in the vertex shader. There's a mismatch between the interfaces. But this value here will be iterated across the primitive. So even though your vertex might set it with a constant color, the raster iterator is going to update that value. And so you get an updated value for each fragment, and we just stick that in the color, and bam, that's what's going to appear on the screen. That's pretty simple. This is virtually the simplest fragment shader you can get, aside from when you set this to a constant value, which is what you saw in the first piece. So if you can understand those fundamental concepts, you're golden. If you start with these kind of things, your programs will come together, and then you just start aggrandizing your shaders to make them do more and more stuff, and life will be pretty good. You'll be doing really great graphics without having to worry about Windows or any of the other bit. Now, Ed mentioned we wrote this little routine called init shaders, and we do this so that you'll feel a lot of gratitude towards us, because the process of compiling a shader is really kind of ugly inside of WebGL or any of the other ones. Any of you write code, right? There's a process you do. You open an editor, create a new file, you type some stuff into it, you close it, you compile it. If you're not paying attention to the compiler, it also does this linking phase, and you go off and run it. So they took that natural paradigm of application development and made it available inside of WebGL for how you compile shaders, except they made each one of those a function call. So here's the sequence that you actually do for writing and compiling and preparing a shader for use. You call GL create program. Well, that basically gives you a bucket to start putting your files into. Think of make directory for where my project's going to start. I create a shader. That's like creating a text file that I'm going to type into. Then I do GL shader source. That's where you type really fast to put all your code in there. Just remember, real men use cat as an editor. That's an old Unix joke. None of you get it, right? OK. Once I'm all done with that, I compile my shader. So that's like taking your .c file and converting it into an object file, your .o if you work on a Mac or Linux or those kind of things, a .obj if you're working on Windows. After you compiled all the different shaders you've got, the attach shader is basically like, OK, now I'm going to link them together. I take all my object files and make them executable. This attach shader is like putting the .os onto the command line when you're going to load them together. And then link program is like running the linker. It takes all the object files, make sure everything works, and gets you your program. And then in order to use the program, well, you call use program. That's dandy, but this is a whole lot of stuff, and we didn't tell you all the parameters that go into each one of these functions. Shader source has like 7 parameters. Why? Well, your shader could be one long string. It could be a sequence of null terminated strings. It could be a sequence of strings that don't have null terminators. You have to path length them. It's ugly, disgusting. You never want to do that stuff. Trust me. I did it for you, and my fee is very reasonable, so feel free to help me out here. We wrote a little function called init shaders. And init shaders takes a vertex shader and a fragment shader. Specifically, remember we're working in the world of HTML. When you want to identify an object in HTML, you give it an ID. So if you remember from way at the beginning of the course, we had our vertex shader that had script ID equals something, and fragment shader script equals something, or ID equals something as well. You pass in those ID strings here, and init shaders will go out, find the shaders, stick them in the right places, compile them up, and it returns back to you either a usable program as an object, or returns back -1, which is kind of universal. Something didn't work right, and this process has failed. So init shaders will fail, and if it does fail, you can actually, the routine will dump out the error logs that come from the compiler. The problem with the error logs is they're not consistent. You can't machine read them. It's like using if you've got 2 different compilers running on the same computer, you're going to get different error messages. Same thing here. So those are meant for your human consumption. And inside of the application, it'll pop up in a little alert window going, hey, here's what the compiler tells you. Your vertex shader blew up or your fragment shader didn't compile. If it does compile, then you just get quietly back an ID that you can pass to GL use program a little later. So, whoop, is that slide in there? No, I'm sorry, hit the wrong key. So there's our simpler way. Now, we've got one more thing to stitch up, and Ed showed you an example of it, but I need to talk through it a little bit. As we mentioned, you run an application, so you create arrays that you pass into buffers, and that sets the data up for GL to do something when you make a draw call. How you get that data into the shader is a fairly obtuse process. You know how to declare shader or variables inside a shader to receive the data, but there's one last piece of plumbing to actually get the values from that buffer into the values that are going to be received inside of the shader. And that process uses a couple of function calls that I'll show you in the next slide. But we've got attributes and uniforms. Remember, those were the 2 types of data that we can put inside of there. Varyings are kind of internal to the process. Your application never sets them explicitly. They're generated in the vertex shader and processed in the fragment shader. So in WebGL, basically, we use a couple of functions to relate those variable names that you declare inside of the shader to the indices that you use to describe your vertex buffers when you were doing the create buffer and bind buffer and all those kind of things. So there's the 2 calls. Fortunately, they're pretty simple. One's called get attrib location, and what that will do is for this compiled and linked WebGL GLSL application, it will query that for a name of a variable that you pass into a string, and it will give you a number back. Okay, great. Got this number. We'll use it in just a second. Same thing for uniforms. It'll go and it'll look for the uniforms inside of this program, return back the location or the index of that uniform variable from the appropriate program, and then we can set values that go into them. Now, for uniform variables, it's actually pretty simple. The value you get back is what you pass in here for index. So as an example, and there are a whole lot of functions inside of WebGL that are GL point uniform, and then these things at the back tell you how to decode the parameters. So for your secret OpenGL OpenGL ES WebGL decoder ring, here's how these work. The number tells you how many parameters you're going to have after the indexing value. So this is the location that came back. And the F tells you the type of these guys. So uniform for F says, here's a uniform variable, goes this point, and I'm passing you 4 floating point numbers. There is a GL uniform 1i, and we'll see that when we talk about texture mapping in just a bit. There's 2F, 3F, 4F, you get the idea. So there's a huge number of function calls for that kind of thing because WebGL is based on a C API. If there were C++, we'd have GL uniform and it figured it all out for us. Yeah, some of our graphics are still banging rocks together. Now, this takes care of setting up vectors and whatnot. It can't set a matrix. There's an additional call for uniform matrix, or for setting up matrices that are uniforms, called GL uniform matrix. Same decoder ring. 4FV says these are mat4s, they're floating points, and all these functions end up with a V. And the reason for this is this mat parameter that you see back here is actually an array of matrices, because quite often you'll wind up passing in a whole bunch of matrices to do things like skinning or variable transformations. You know, your model view matrix might be in one and your projection matrix in another. We'll talk about what those terms mean in a second. It's a function call. You can read the manual entry on it. It works a lot like this, except you stuff other data inside of there. One other important point is this is a variable called transpose. One thing that always will goof up people working in GL, whether it's OpenGL, OpenGL ES, or WebGL, is the matrices are not written the way C programmers think. C programmers think your variables go across the first row of a two-dimensional array, then they wrap around and go around the next one, and the next one. The guy who wrote the OpenGL spec a long time ago was a mathematician, and he was very much a purist about these things and said, C programmers, who are the bastards of the earth, write their code like this. No, no, no. Mathematicians think in column vectors. So index 0 is the first point, index 1 is the next element in the next row down, the next element in the next row down, and so they're column vectors. Well, it turns out this is transpose of what C people want to do. Well, in regular GL, there's a routine called transpose that will take your data and transpose it for you. Unfortunately, they turned that off in OpenGL ES because that's extra computation. Look, if you know what the problem is, we're not going to solve it for you. You fix your code yourself. That's kind of the mantra of how OpenGL goes. We're going to do the bare minimum for you, and you can stab yourself and cut yourself on the sharp knives all over the place. In this case, this routine will fail if this variable called transpose is not set to true. Is that right? I think that's supposed to be set to false. Ed did admit that he went out last night and enjoyed some libations while doing his dinner, so we can see where that came on. No, this has to be false, dude. Trust me on that.
Oh, it's true. It must be false in...
You're going to confuse him. You can't say true and false at the same.
Yes, right.
Sorry, we're segueing into the Laurel and Hardy show. We'll come back to the regular slides in just a moment. Yeah, most people, Laurel and Hardy, yeah. Look at 50s comedy. It's good. Read the manual page on this part. This is how you set matrices. They're slightly different for that. We'll see another use of this when we get to texture mapping. So, good. I'm on the last slide for this section because that was a lot of stuff to contain. Here's how we break up our code. The HTML file contains the shader source. You think I said a bad word. No, 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 no. It's a family-friendly show here. Contains the shaders. They fall in script tags, right? You've got a vertex shader tag and a fragment shader tag. Come on, my folks are in the audience. I'm not going to say any bad words. All the utilities that are inside of there, we've separated out into JavaScript programs, and they're loaded as a linked reference to a JavaScript, right? Another line, you know, script, source equals name of file, pull them in that way. That just helps us organize our code a bit better. You describe all your page elements, all the things that are inside of there, right? So you're actually writing your application in the HTML. All your interface elements and things like that are written into the HTML part. And most importantly, it contains your canvas element or the multiple canvas elements that you might do for a multi-window application. So if you look at our examples, that's where we put in the HTML file. Our JavaScript files contain all the executable code that actually runs all those different pieces. The first thing we will do is when you do HTML, and this is kind of the odd thing, right? Most of us are either C programmers and not web programmers, and most web programmers are not C programmers. If you pick this up, you become creme de la creme of the crop that you can do HTML and you can write code. Because you kind of get one or the other, but not both doing really well, and most people don't understand 3D graphics in HTML. That said, the window.onLoad function, we always set to this routine init. So init is where we initialize all our GL stuff. The first thing that function does is get the canvas. The next thing it does is create a context. After that, it's all WebGL and data buffers and other sorts of really odd and nefarious things, and takes care of all of that. Then we have a little routine called render, which actually takes and draws the scene for us. Now, one important point that isn't really called out anywhere well is OpenGL ES, and by virtue of that, WebGL, is always double buffered. They show you one picture, and they draw another picture in the scene, and then when it's time to go, you swap the buffers. If any of you have ever written a C program that uses OpenGL, you know there's a swap buffers function, whether it's glut swap buffers, or WGL swap buffers, or GLX swap buffers, or any of the other things. inside of JavaScript and HTML and WebGL, your buffer swap is implicit. They don't make you make a function call. When the rendering routine stops, there's a implicit buffer swap at the end of it. So you don't ever have to call it because there's no function for doing it. It just happens. And that's how this works. So our render routine basically will start with a clear, and it'll do all the rendering. And then when it exits, we swap buffers, they display the new picture, and we're off and going.
I'll talk about this after the break, but I did want to show you a few examples that will emphasize some of the points that we were just making. So let me see if I can actually switch in to my examples. I like to show this example, which you may not appreciate till the end, but this is one of my students did this last semester, and it sort of points to the power of the GPU. That we talk about when we think about, oh, well, this is just a different way we're going to do our graphics. This is what's called a Voronoi diagram. And what it's doing is creating, if you freeze it for a second, for each set of vertices, there's like 100 vertices in there, it's computing the distance from each point in that array in the display to the vertices and then doing a coloring based on that. It's a shortest path. But that means for every iteration that you're seeing, this is going along at about 60 frames a second, for every one of those, this is, I think, a 512 by 512 buffer, it's doing a calculation from every point in it to every one of those 100 vertices. And how is it doing it at this rate? The answer is it's doing it in the fragment shader. That the fragment, on a modern GPU, you may have literally hundreds of independent processors on it. And each of those is handling a fragment. And every time another fragment comes out of the rasterizer, it's saying, oh, is there a processor available to process this fragment? And if there is, so this thing is going at a rate that you would never get on your CPU because you basically just have the one processor on your CPU. So you're sort of getting this kind of stuff for free. This isn't even really a graphics problem, but it's really a great example to show you the kind of power you get by essentially moving what looks like C code off into a fragment shader. And all you do in the application side is send over a rectangle. And the rectangle automatically generates through the rasterizer all of those points on the display. And it says, well, what do I do for each fragment? I run a fragment shader. And the fragment shader does this calculation and computes a color. So some of the things, I could show you a lot of other examples. I'll give you my website. There are others that that are just, you don't think of as being a graphics problem to start with, but when you see the power of the GPU and your ability to access it, you start thinking, oh, I ought to do this on the GPU. Now let me show you a couple of other examples, just because we've been talking. Actually, I just want to show, I think, this one. Okay, this is the cube, which happens to be rotating here, and it's a good example of a couple of things that Dave was just talking about. I can change, I'll show you after the break how we change the direction of rotation and things like that. But the points I want to make here is, one, this is showing exactly what the rasterizer does. This is the example of the cube, and what we've done is we've sent a color for each vertex. Now, why don't I see solid colors? Because the rasterizer is interpolating the colors at the vertices across the surfaces. So each of those faces of the cube is actually two triangles. Each of those triangles has three vertices. Each of those vertices has both a position attribute and a color attribute. When that information gets to the vertex shader, unless I decide to do this problem some other way, automatically the rasterizer is now going to interpolate those vertex colors into colors across for each fragment. And so that's where you see these varying variables come through. We had that little shader that was saying, take the colors and send them on to the rasterizer, and out they come in the fragment shader. But what's coming out in the fragment shader is not what you put in, but rather an interpolated value, and that's what you see going on here. Now, the other thing you see going on here that's a little more subtle is there's also a uniform variable in here. So the attribute is the color, but there's a uniform variable because we want the rotation to be incremented a fixed amount for the entire object. not for each fragment that comes along or each vertex that comes along. So we're using a uniform variable to periodically update the angle at which we rotate. So both of them are in this very simple program, which is just a very simple extension of the program that I showed you earlier. So we'll see some more examples of these things in the second half, but I thought this would be a good place to stick them in now. Okay, actually, there was one more thing I kind of wanted to mention for those of you who are, there's a whole bunch of little JavaScript things we could probably spend the hours talking about that but there are a few to keep in mind. And one of the issues with WebGL, because working in a browser environment is always security kinds of issues. So some of you might have said, well, why don't you just read in those JavaScript, shaders is just ordinary code, and that's turns out is not that easy in JavaScript. And in addition, with browsers, there's some security issues. So we had another version that's on the web of the init shaders, which actually reads the shaders in from files, which are pure text files, because that's all, the shader code is pure text, and the drivers compile that. It turns out that that can be problematic depending on how you're running and from which browser, because it's one of the issues that security people in the browser world worry about, and you can't let code read in arbitrary files from places. And so if I have examples of that on my website, and that'll all be posted, and we'll post this course up there. But you may find that for example, if I run the version that simply reads in two text files for the two shaders, Chrome will say that's just called a cross-origin request, and it's a violation if I run it locally. But if I put everything on a remote server, then it's okay because it's all running from one place. So you may find some strange things happening that are security issues that people who work with OpenGL in the past, including me, we never had to worry about those things, because you ran a program, you compiled a program, it ran locally, and you didn't worry about anything else. Now you're in the browser world, and things are all over the place, and that's something that can be pretty scary. So as you start making those, switching over to WebGL, which I find, having taught with it for the first time, the courses I've been teaching for a long, long time, it was the best experience I ever had in terms that we just did not have all the issues you always have at the beginning, for those of you who teach, of trying to get these libraries going and which version, and whether somebody had a 32-bit version or a 64-bit, and where did Linux put these libraries. That stuff all went away. I didn't have a single question from anybody this whole semester on any of that. It just worked because it worked within the browser world. So there's some enormous advantages to taking this route, but at the same time there are some gotchas that come up along the way. Okay, so let's talk a little bit about buffering and interaction. And here's again, I think, really where you see that the advantages of going to a browser-based system. If you were trying to do, the other thing was missing, I mean, as Dave said, well, the hardest thing was to open a window. Well, the second hardest thing probably was to get any interaction. And so what a lot of us did, especially if we taught the stuff, is, well, we used glut, because glut could be recompiled on different systems, but glut was getting kind of old, and glut, in fact, shouldn't be able to work on any modern OpenGL that's purely shader-based. So we try to use free glut or GLFW or something. And it was just sort of problem after problem. And you always had to recompile and did the lot. That stuff's all gone now. And so let me show you a couple of examples here. First, I'll talk a little bit about buffering, but then I want to just show you a couple examples of just how easy it is to get interaction, even if you're not going to use one of the standard packages like jQuery. That with just two lines, you can put a button or a slider on that's useful, and I'll show you a simple example of that. So let me talk about that. a little bit. So Dave started to talk a little bit about the issue of double buffering, and I think the main thing here is that it's happening, as Dave pointed out, it's happening automatically, that all browsers double buffer their displays. The question that comes up for you is, well, if you want a little more control of that, if you want to slow things down or speed things up, what do? Well, the buffer, and in general, if you look at the speed, it's easy to put in a little speed detector into your code. The browser is going to go at 60 frames a second. So that's and if you should be pretty happy. Usually you're happy with that. So what happens if you want a little bit more control? Well, generally what we'll do is for non-static applications, we simply put request animation frame at the end and just call itself. So it says on the next refresh cycle of the browser, it's going to re-display and go through your render function again. That's usually the easiest. Now, if you want to slow it down a bit, then you have a simple function like setInterval that says what function should you call. It'll generate an event, and I'll talk a little more about event-driven input in a second. It just says, after how many milliseconds do you want me to execute this function? So I can slow down things very easily that way by just putting this one line in my render function that just says is a delay. So that works very, very well. So here's a real simple example of that, where what I'm going to do is I'm going to change the size of that cube and just make it bigger and smaller. So this is an example of a vertex shader, where the vertex shader is actually changing, not simply passing through the values of the vertices, but changing the values of the vertices. So what you see here is, let's see if I can point this in the right direction. So here's our render function. It's clearing the color buffer, and here's the depth buffer. It's getting a rotation angle as a uniform from the application, increasing increasing the time variable, and then it's getting uniform. It's getting the time. It draws the arrays and then requests an animation frame. So this is sort of a standard render loop that just gets the time, rotates an amount that's based on what you send it. But here's the point I'm putting the vertex shader. I'm changing the position sinusoidally. I'm using that time that I sent in as a uniform. Okay, and I'm using it to now just sinusoidally change the vertex position, and it's making things bigger and smaller as time goes by. So it's a totally trivial change, but it points out that some of the things that you can use your vertex shader to do. Okay, so the vertex shaders, what do we use them for? Dave talked a little bit about this. We change vertex positions. If you want to do morphing, you want to morph one object into another object, generally what you'll do is you'll do some sort of an interpolation in the vertex shader. More often it gets used for transformations. So when we look at rotation, Dave's going to talk about transformations. When we talk about things like rotating that cube, the positions are changing, and it's usually almost always best to do those positional changes in the vertex shader or sometimes in the fragment shader. Lighting. If we do lighting, then we're going to change the colors at the vertices, but change the colors based on a model of how the materials reflect light and where we place lights in the scene. Where is the best place for that to happen? Well, the worst place for it to happen is in your application. We can do it either in the fragment shader or in the vertex shader. So you'll see both. We'll just talk about that a little bit in a while. But those are pretty much the kinds of things that one does in a vertex shader. Now, let me turn to talk about event-driven input. How many of you are familiar with programming event-driven input? Yeah, I see about half of you. What we find is that it's changing somewhat, but if our students, for the most part, they're not familiar with event-driven programming at all, and that's one of the things in teaching OpenGL. You have to teach them about events and event handling and using these libraries. In the browser, it turns out it's very, very easy. So I'm going to look at a couple of things: mouse, keyboard events. Pushing a key down, getting back which key was pushed. Noting that the mouse was clicked, perhaps getting back which button of the mouse that you used. I'm not going to talk here about window events, but things like what happens if you change the size of a window, how do you handle resize events, it's the same sort of flavor. Menus and buttons I'll talk about a bit. They're very, very easy to do. But the basic model is a callback model, that each event generates a call. There's a function assigned to each event that you want to deal with that's called a callback. It used to be called a callback in the X community. Now in the browser community, we call those things listeners. So the program sits there, and that's sort of the execution model that happens when you're running in HTML. It goes through the code and it just sits there. And what is it sitting there? It's sitting there waiting for events to happen. And if an event happens, whether it's a mouse event, a window event, or any other kind of event, if there's a callback or a listener that's registered, it then executes the code that's in that callback function or event listener, and that's our basic model. So here's some really simple examples of setting up a button. So I think you saw as I showed you that rotating cube, I'll show it to you again later, is I had 3 buttons on the screen. Actually, I could put a 4th one up there to just stop it from rotating, which just says, okay, there's a button. See, here's where, again, the integration with HTML is so important. There's a button element in HTML. You don't have to worry about creating a button. You don't have to worry about some library in there. As part of HTML, there are buttons. So I say what I want to do is create a button. Okay, so let's create 4 buttons. One button is I'll just give it and again, the ID is so that I can identify it in the JavaScript code. Okay, I could do this all in the browser, but it's again this separation where I'm trying to do the setup stuff, put that all in the HTML file, and put the action part. What do you do with the buttons when they're clicked in the JavaScript file? So this gives me an ID to refer to it. This is the name, the code that appears on the button. That's the end of that button element. And I do the same thing for a Y rotation. So these 3 buttons are just going to say, are you going to rotate about the X, Y, or Z axes? I just switch between them, so they're simply buttons. And then I have a 4th button that says, okay, if you don't want to rotate, just click on that button and it'll stop the rotation. So 4 buttons, that's all you have to change in the HTML file. Go over to the JavaScript file. Now here's where the listeners go. So I have a listeners that just say, and these are 1 line each. Each button is 1 line in the HTML file and 1 line in the JavaScript file. It says, okay, go get, here's setting up that listener. It says get the button that's called X button, that's that ID. And I want to say on click. So HTML understands, and JavaScript understand certain types of events. On click just says when you've clicked the mouse. So on that click, if that's the button that you clicked, here's the function I want you to do. And all it does is say that the present rotation axis is going to be the x-axis. Likewise, for the y and the z, if you click those buttons, then you'll change the axis to be the y or the z axis. And if I click on the toggle button, it just says, I'm going to have a flag that says whether I want you to rotate or not. And so I just negate the flag, change it from false to true or true to false. So these are 2 lines for each interactive device I put on. And for those of you who have done, desktop OpenGL before, I don't think you've seen anything any simpler than that to create interactive devices. Sliders, the same thing, pair of lines for each slider that you want to create. So let me see what I have here. Okay. And here's the render function, just to show you how I use that in the render function. So here's the clear. Here it says, if the flag is true, then I'm going to increment the rotation angle. And the rotation angle changes an array which says what are the angles that I'm at. So it increments the one for the axis I've chosen by the last button push, and then increments that by 2 degrees, and then just draws the arrays. That's it. So again, easy to do, request an animation frame at the end, so it just keeps render every 60th of a second. Okay, so let me show you one example before I let Dave talk about transformations. It's coming up quick, Dave. Let me come back, show you an example of this. Yes, here. Okay, let me make this a little smaller. Ooh, too small. Okay, so can you see that at the bottom? Yeah, so here's a texture map cube. I'm going to be talking about texture mapping later, but this is just the buttons changing direction of rotation and stopping it. So this is exactly what you saw. I want to show you this other example, though, give you a little bit more. Let's see, is it this one? No, it's this one. It's this one. Okay, so here's one where I sort of have, again, I have a menu, very same thing, just put the entries in the menu. You have a callback function that corresponds to each element in the menu. Now this is using the timer. So this is saying if you want to make it slower, just put a delay in. So if I want to make it slower, I can just put in more of a delay. If I want to speed it up, I'll put in less of a delay. And if I want to go the other direction, that's just a button which changes a flag which says whether you increment the angle or you decrement the angle. And you could do exactly the same thing with a slide bar. I don't have the code here for it, but again, it'll be on my website. That just is, again, 2 lines. One line to say I want a slider that goes in the HTML file. What are the parameters on the slider? Where do you want the bar to be to start off? And then on the other side says, well, what do you want me to do when you slide it? If it's over here, I make it faster. If it's over here, I slow it down. And again, this is without using any of the standard packages. So these are the defaults. There's a default slider, there's a default menu, there's a default button. They're not pretty. If you want prettier stuff, then use CSS and jQuery, the standard packages that everyone uses on the web. But if you just want to get some stuff working, you have an application you want to do, this WebGL, I feel, just makes it so much easier to do. So let me turn it over to Dave to talk about transformations. And I think you're here.
So, for those of you who were before the break, if you remember, I mentioned trigonometry and all that stuff. Yeah, get ready for a flashback. Okay, so inside of WebGL and 3D computer graphics in general, everything is really powered when you want to take this 3-dimensional world that we live into and splat it down to fit it on the screen using 4x4 transformations. And all these things actually do is take one space and convert it to another. And you'll hear us talk about various types of transformations. The good news is there are only 3, and they're not that tough. You'll use one of one, and then you kind of use one of the other, and then a whole bunch of the other ones, but it turns out the last 2 are kind of almost the same. I'll explain exactly what that means in a moment. But this is what we call the transformation pipeline. And this provides a conceptual model of how you might want to think about all the transformations that a vertex will go through in getting from the 3-dimensional world that you've modeled, however you've done that, whether it's graph paper and a pencil or using Maya or Unity or some other modeler kind of thing, down to figuring out which pixel inside the viewport is going to light up. So your vertex data is what you stuff into a buffer over there. And generally speaking, you'll hear Ed and myself use the term model view transformation. A viewing transformation, which we'll touch on in just a moment, is kind of where the scene is being viewed for. Imagine where your eyeball, or your pair of eyeballs, is looking into the scene. You're kind of at a particular point in space, and you have a view direction that goes along with it. That's what we call the viewing transformation. A modeling transformation are the things that you classically think about. Most 3D objects, when people ask, what are the standard transformations, they're scales, translates, and rotates, right? We'll talk more about those, and I'll show you examples of what they are, and more specifically, I'll show you the math that's required, because you have to do all this yourself. With shaders come great power, but also comes kind of a whole lot of responsibility and inconvenience, in my opinion, because you need to kind of write all this stuff and get it working. Good news is there are ample libraries out there to take care of all of these things. But what's important for this part is knowing the sequence of things that happen. So modeling transformations, you might, for example, move something to a different location in the room and scale it or rotate it to get its orientation correctly, right? If we wanted to take the chair in the front row, slide it over here, and bend it to face the screen, that'd be a translation and rotation. Those all kind of get glommed together, and after the model view transformation, all you've done is really move space around and maybe stretched it or squished it if you've applied some scales, but it's still three-dimensional space. The transformation of taking the world we have and smashing it down to fit on a two-dimensional screen is the job of the projection transformation. And turns out you only have one of those, right? For humans, your projection transformation is the lens in your eyeball. It's the part that takes that and projects it back in your retina. The matrices that we use for doing this, they have analogous kind of ways they operate. In the end, they're just 16 numbers with a couple of zeros inside of there that explain kind of what you've got, right? The photography metaphor works very well here. If any of you are photographers, right, you've got your field of view, basically how wide you can open the aperture. And then you have, well, most cameras have a circular aperture. But if you imagine a camera that had a square, you have your aspect ratio. Basically, what's the field of view in one direction and the other. And that has to match your window. We'll talk a little bit more about that. Well, this projection transformation is another 4x4 matrix. The pair of these, or whatever this winds up being from this collection, are all processed inside of your vertex shader. You take your vertex and multiply it by the model view matrix and the projection matrix, remembering that it gets multiplied on this side, and the order of these guys is the reverse order as you write code. So basically, you'll have some code that says GL projection equals my projection transformation times my model view transformation times my vertex data. It's exactly the opposite order of this stuff. But once you do that, the rasterizer will do this little operation called perspective divide. And the reason there's a W there is that W is what enables all sorts of capabilities, in particular what's called a perspective projection. When you're using your eyeballs and you look at things, like if it's a car and it's driving farther away from you, it gets smaller. Well, actually, it looks like it gets smaller, but the car really doesn't change size, right? That's kind of a byproduct of how your eye works, and the projection transformation that your eye uses to do that. We've been able to model the same thing, and this W parameter, basically that extra coordinate in your homogeneous coordinates, is the one that enables this. The projection transformation will set W to the right scaling factor as an object gets farther from your eyeball. It's kind of cool. It's a lot of fun to play around with once in life, and then you go, okay, got code to do this, ain't touching again. There's another piece that happens here called the viewport transform. Now, the viewport is the part of the window that you can draw into. Now, sometimes you go but I can draw into the whole window. Well, that turns out because your viewport's the same size as your window, but there's no requirement for this. You can say, I only want to draw in the upper left-hand corner and set the viewport just to be that part. So if any of you have, for example, looked through our textbooks and seen the historic chapter on using CAD packages, they'll have a window with 4 different views in it. You have a perspective view, and then a top view, a side view, and the other side view. Yeah, you get it. We can do that using viewports. We just take our window and carve it into 4 pieces, controlling which part we're rendering into. And the viewport transformation takes care of mapping your projected space into that part of the window. You just set one call, which basically is done in pixels, going, the viewport starts at this pixel in the window and goes for this width and this depth. Piece of cake. And out the other side, you get your 2-dimensional window coordinates. Now, having said all of that, we'll take a look at this from another different way as we introduce the different types of transformations we've got. We'll talk about projection transformations, and this really is akin to adjusting the lens on a camera. It controls how much of the world you can see, what the field of view is, and what the aberration, what the aspect ratio is in controlling how this looks. The important part of this, and I'll remind you again about that, is the aspect ratio of your projection transformation. As compared to a camera, which I said is kind of a cone, this is more like a pyramid. It's a square pyramid that goes along with it. And the aspect ratio of that pyramid has to match that of your viewport. Otherwise, you're going to get a distortion. You draw circles and they look like ellipses, you'll know what I'm talking about. We'll talk about viewing transformations. So we'll talk about a couple of different ways that you do that. One is like if you're writing a flight simulator or you want to have a first-person shooter game, this is the kind of thing you use to control where the eye point is moving in the direction it's looking. We'll talk about modeling transformations, which affect the various models and how you might use those, and then we'll just touch on the viewport, which is simple enough. Now, the core bit of things that you need to know about this are matrices are 16 elements. They're 4 by 4. And if you're here before the break, I said, you know, the guys who wrote this didn't like C programmers. He must have been a Fortran programmer in addition to a mathematician, because they've changed the order that most of us would think in. This is one of the things that, you know, I've been teaching GL for the better part of 20 years in various formats. This is like bug number one. People get their head around this because they do it the wrong way. If you line up 16 values to make a matrix, so whether you use our mv.js class and just generate your own mat4, goes along with it, or you do it inside of the shader, remember this slide. These slides are up on Ed's website because this picture is worth 1,000 words. Here's M0, and it goes down the column as we go through the various pieces. Okay, you get that part. The other thing, as I mentioned, always remember to multiply the vertex on the, got to get this right-hand side of the matrix. I don't know my left from my right, and I failed at that part. If you put it on the other side, perfectly acceptable code, perfectly unacceptable results. That said, all the transformations I've just discussed, you have to manufacture these matrices yourself. The good news is if you grab our mv.js thing, we're not promoting a product or anything, we're just lazy. And so we put all this together, made sure the math is right, and it can just make your programs run a lot, or be a lot simpler to put together. So how do you actually do this? When you think about this, you work through the pipeline backwards. You want to set up how much of the world you can see first, and then you want to position your viewing frustum, that is the part that expresses your projection transformation. You want to locate it in your 3D world, right? You're in a world that you get to see things that are out the direction of your nose, unless you're a little different than I am, right? There's stuff behind me, clearly, but I can't see it. My viewing frustum emanates from my eye out this direction. And I get to see things that kind of cover my peripheral vision. So the viewing or the projection transformation does exactly that. It sets up how much of the world you can see and, well, what the aspect ratio of that will be. We'll get there in a second. And the other part of it is then we use the viewing transformation to position that projection transformation in space. So the projection transformation is going to carve a part of the 3D world out. Anything that's inside of there gets put into the screen. Anything that's outside is clipped out of the viewport. So your projection controls how much of the world you see. The viewing transformation controls where you actually put it. So OpenGL uses something, well, they use what's called eye coordinates. After you apply your model view transformation, you'll be in what are called eye coordinates. And I keep saying eye coordinates because the concept is important. You'll hear people talk about it, and it describes two particular scenarios. Eye coordinates position the eyeball at the origin, and you're looking down the minus z axis, right? And there are a whole bunch of things that are predicated on that. A projection transformation, as you remember, carves out a chunk of the world. It's kind of it's a truncated pyramid if you're doing a projective transformation, or a perspective one. It's an actual cube if you're doing orthographic. I'll show you some images of that in just a second, right? The distances from your eyeball to these, what are called near and far clipping planes, and I'll illustrate them in just a second, are positive distances down the negative axis. So eye coordinates are important because if you don't apply any modeling or viewing transformation, you just set up a perspective transformation, you need to know where to actually put your objects to be able to see them. And you have to move everything down the minus z axis to get it done. As you experiment with this, if you're just starting out doing 3D graphics, you just kind of plug in some numbers and go like, oh, I thought I was going to get a box over there, and I didn't. And you go, why isn't the box the right shape? Or why isn't the box there? A lot of it is, in this case, a sign mistake. But we'll tell you exactly what to do and how to avoid those problems. These 2 points are really essential, though. Your eye's at the origin in eye coordinates, and you're looking down minus z. Now, as mentioned here, the projection matrices use a 6-plane model. It's a cube or a truncated pyramid, which just means some part of the cube got shrunk in the top. You've got a top and a bottom, and then the 6 faces around the side. The top and the bottom, well, let's think of this as distances from your eyeball. It's what's called the near and far clipping planes. Let me pull up the following pictures. So, in this picture on the right-hand side, that's right, yes, this is a perspective projection. And objects that are farther away appear smaller in the viewport. So here are the interesting and important things to know. This little piece up here will be the near clipping plane, and the piece in the back is the far clipping plane. They're measured as distances from where the eye is located down this way. So, if this is 5, this might be 15. They're distances which have positive values, even though the axis that goes from here through the middle of the perspective projection is down the minus z axis. It's a left-handed coordinate system. Why didn't they do right? Because the guy who did this designed theater, and that's how they do it in theater. You stand on the stage and z goes out into the audience. You wanted some perspective on how these things come together? There's no rational reason. Somebody picked one. Okay, good. So the other part is, you see that the near clipping plane here has a little image rendered on top of it. That image there is the viewport. So the viewport gets mapped to the space that the near clipping plane carves out. Now, you remember, the viewport's a square, and this thing on the viewport is some rectangular shape, which might be a square. This shape in the near clipping plane, when controlled by these 4 other planes, is going to be some rectangular shape. If the aspect ratio of those 2 rectangles don't work together, if they're not equal, you get distortion in your objects. So just something to kind of realize. Now, if you want to use a perspective transformation like this, which is exactly how your eye is, so if you're doing first-person shooter or anything where you're not doing engineering where you need to preserve angles, you want to use one of these guys. And you need to generate this particular matrix here. Now, this matrix is filled with all sorts of letters, which are very amusing, but let me decode it for you. N stands for n, which is the distance from the eye to the near clipping plane. For those paying attention, f is the same distance going out to the far clipping plane. Then we have left and right, L and R, and that is the distance basically from the center point over to the edge of this thing. That would be, L would be the value for that side, R is the value for this side, B is the bottom, and T is the top. So if you look at those, you've got these values here, and that generates this 3-dimensional matrix. We have a function in our library called perspective, which you give it basically a field of view angle, which is the angle between this top plane and that bottom plane. We like numbers like 60 and 75 degrees. You give it an aspect ratio, a near distance, and a far distance, and it does this math for you automatically, and you never have to look at this again. And you'll like me for that, right? Now, the other type of view is what's called an orthographic view, or an orthographic projection. And that is basically like we take all the objects in the scene and smash them flat. So you put them in your AeroPress and now, everything there is, regardless of its distance from the eye, will have exactly the same shape. So it's an orthographic or infinite projection on those things. But it's the same kind of mechanics. Near clipping plane, far clipping plane. Now, in this case, those values aren't quite as well defined because the eye can sit anywhere along this line. But let's keep everyone on the same page. The eye is always the origin, and your near clipping plane is a distance from that. That just controls where objects need to lie between these 2 planes. Near and far, same thing. Then you have, left side, right side, bottom and top. And it carves out, in this case, a square. And if you look at this, you can work that math out pretty easily. It's just like taking a line segment and stretching it and moving it to a different place. All that guy does. Well, we have a routine for that called ortho, which will generate that matrix over there. So all these things are built inside of there, but if you feel like understanding them or wondering like why did everything go away, you can actually peel them back, look at the mathematics inside. Now, in your application, you'll want one of those. You'll put your projection transformation in the scene, and that will control how the camera is rendered for that frame. Let's say you're doing, some kind of game or something where you're simulating somebody looking through binoculars. So you've got your view from the binoculars, and you want to zoom in. One way you might zoom in is decreasing the size of the viewing frustum. Because remember, the viewing frustum gets mapped out to the viewport, so you've got less information in there, but now it's going to cover a bigger space in your screen. So that's one way to do it. So you can change your projection transformation every frame, no problem. You just update the matrix. But you want all the objects inside of your scene to all be rendered by the same projection matrix. Consequently, you usually put your projection matrix as a uniform variable that's applied in your vertex shader. Stick it in there and use the same one across all your different vertex shaders to get things going. Same with this next one, which is a viewing transformation. Now, if we use a camera analogy, which we kind of alluded to here, the projection transformation controls the lens. The viewing transformation controls where the tripod sits. Where's the camera located, and what direction is it looking at? Well, it turns out we wrote, and we didn't write any of this, we just kind of ported the functions from the predecessor of OpenGL, called IrisGL, had a library that had these functions in, and people have been using them for the better part of 30 years. They just keep getting reported to all the new graphics libraries. So we kept the same name, lookat. And lookat takes 9 parameters, but really it's 3 vectors. The first one is the position of the eye in XYZ space. You pick a point in your world coordinates, go, eyeball sitting here. Great. That's where the camera goes. the look value is the point in space you're looking at. So for example, I might be looking at the camera. So there's some location of the camera, my eye is here and that. If you take the difference between those 2 points, you get what's called the line of sight. Line of sight's from my eyeball out to the point I'm looking at. Fair enough? Well, what the viewing transformation does is bring and align the projection transformation down your line of sight. If your left value is equal to your right value and your bottom value is equal to your top value in your projection transformation, you get a symmetric pyramid around the line of sight. Now you can do kind of things like, my viewing frustum might look like this, but there's absolutely no reason why it couldn't look like this. Now you go, why might I do that? Well, a long time ago we used to do cockpit simulations where the fighter pilot's looking this way, but in his peripheral vision you want that kind of distortion that stretches things out in the sides. You'd use an off-axis viewing frustum to do those kind of things. Generally speaking though, most people look in this kind of stuff and keep it symmetric. Fair enough. So look at says, I position that and brings the viewing frustum actually in there. The last 3 values are what's called the up value. Because if you look at this, there's nothing that controls rotating the projection transformation or the viewing frustum around the line of sight. So we specify what direction is up. Normally up is what would be the vector you want in the scene to point towards the top of your monitor. Quite often if you're doing kind of like X and Z is on the floor and Y is going up, which kind of matches what you would think about in a 3D space. So if you put your X, Y, and Z out right-handed rule, X that way, Z that way, Y comes this way, that would be your up vector. So you do 0, 1, 0. You can modify that, so if you're writing a flight simulator and you need to do a barrel roll, you just kind of take your up vector and rotate it around. Up still points towards the top of the monitor, but your world tends to do the opposite direction. You know, this is relative frames of reference. So lookout's a really popular way of doing things. If you're writing first-person shooter games, if you're writing any kind of simulator, whether it's boats, trains, automobiles, whatever, that's probably the part you'll use, and you'll just update the eye and the point you're looking at, and perhaps the up value if you've got some role in the scene, and that will take care of all the different parts. We have a little method, lookout, that takes those values and generates that part. Matrix is completely uninteresting, not even gonna bother showing you. Actually, that's a big fat fib because the math is about yay long, and it uses all sorts of weird mathematical constructs, outer products of matrices and stuff. It's really good for looking at after a beer or 6. Anyways, we won't go there. Now, let's talk about modeling transformations. It turns out your viewing transformation is actually just a bunch of modeling transformations put together, and I'll explain what it is in a second. But inside of GL, which we've kind of patterned what's in the MV library, they used to have 3 different types of transformations they do. One's called a translation. Picks something up and moves it. Now, if you remember, and we're paying attention about 6 slides ago, I said transformations actually change coordinate systems. When you think about this, you're going to go, oh, I drew a chair, and I want to move the chair. Well, in OpenGL-based computer graphics, or actually almost any library that winds up in rasterization, they don't move objects. They move coordinate systems. So, a couple of tips. When you're modeling a scene, model things around the origin. Because what happens is, instead of moving a chair, you actually move the origin and then draw the chair around the new origin location. So a translation, as you see here, actually takes a current coordinate system, so let's say that's there, and locates it to a new spot. And then you render with respect to the origin of that the newly transformed coordinate system. May take you a little while to get your head wrapped around, but it's basically the same as, you know, if I look at the room here, and then I move my body to somewhere else and look at the room, everything looks like it's shifted. Well, that's either me moving or all the chairs moving. In this case, this is just the origin moving. It's like taking the world and moving it to a new spot. So translation's simple enough, and yes, there's a translation routine. But you know, you probably can construct this matrix even after the aforementioned 6 beers without too much trouble. Now, scale is the next one. Scale stretches space. By default, any coordinate system you're working in GL has the same spacing of points in the X direction, the Y direction, and the Z direction. A scale allows you to modify that. So scales bigger than 1, increase the size of space. Scales less than 1, shrink space, compress it. And scales of 0 are just bad, because scales of 0 make things disappear. It's kind of like a black hole, but you can get them back, just don't do 0. If you do 0, well, life gets a bit less interesting. Now in this one, there's a translation applied, but here's our original coordinate system, and this is our new coordinate system. We've scaled Z by a factor of 2. We've stretched space. We've shrank y by giving it a value smaller. And if you give it a negative value, you can reflect space. So the x-axis used to go this direction, but by giving a negative value, we can reverse the order. So fair enough. Look at any graphics textbook. This will all be fine. Here's rotation. Rotation basically takes a coordinate system and rotates it a particular number of degrees around an axis. The axis can be anything coming out of there, and it'll just twist space around it. The mathematics for this are enough to make most people run away in panic, so we don't bother to show it to you. But rotation's taking spin stuff. And there's a routine in there that basically says, around this axis, rotate by this angle. You get a matrix, you multiply it in, everything's good. So let's look at this in code. So here's the vertex shader for the cube rotation part. So we have some attributes varying and our uniform theta. And theta is a vector of angles that represent the rotation around the x, y, and z axis. So the application will set those up and pop it in, and then we'll use those constant values to modify every vertex that goes along with it. Now, a lot of the things that happen to the vertex shader are vector-based kind of operations. So here we take the value of theta that we passed in and convert them to radians. So there are 3 angles in there, and all of them are automatically multiplied by pi divided by 180, and we get the various angles back. We do cosines and sines. Well, what this does is takes the 3 values in here, applies the cosine operator to each one of them, and we get the values in for C and S. Everyone with me? Looks like regular C code, except there are operators in there that know how to expand out and work on all the different pieces. And then we go off creating some matrices. So here's a rotation around the x-axis. And if you look in any graphics textbook, you'll see what's going on there. Remember, here's our the 4 values that go here represent the first column. The 4 values that go here represent the next column. The 4 values here, so on and so forth. So this is just the normal rotation of cosine and sines for rotating around the x-axis. I'm sorry, yes, it's really gross, because you're like, why doesn't the library take care of this? I can't do anything that's not politically correct to describe the answer to that. So you can generate these in the shader, you can generate them in the application and pass them in as uniforms. Take your pick. This makes a really nice example. So we have a rotation around x, we do the same thing for y, just note the new positions for the rotations around y. Since we're a very predictable bunch of guys, we have a rotation around z, you get it? Here's the important one. We take the position and we apply the x rotation first, then the y, then the z. Remember, your vertex goes on the right-hand side close to the semicolon, and everything else goes in the opposite order across it. This is just a projection. Now, the rendering that we were doing in that one is using a very simple orthographic projection, right? We're rendering actually into normalized, what's called normalized device coordinates. That's that -1 to 1. To keep the math simple, we don't apply a projection transformation. But if we did, projection transformation would sit right over here, right before the equal sign. And we can generate it inside of there, or you can pass it into the application. Now, a little tip. I spend a lot of time in my day job looking at how people write GL code. And while this one is, well, this is kind of intriguing, right? Because this operation is going to be done per vertex. And you look at this and go, great, I'm multiplying 3 matrices together. Well, if you do a matrix multiplication, right, it's an order n cubed operation. It's a lot of work that goes on there. Now, if you compute these in the application, that is in the JavaScript code you do, multiply them together, you can reduce this down to a single matrix multiplication. It's an optimization. A lot of people don't do those, and GPUs are bloody fast, that's great, but if you chuck a couple of million vertices like somebody came up and talked to me about, this overhead actually becomes significant. So one of the optimizations that's easy to do is take and compute the matrices in the application, do the matrix multiplication together, and just pass the single result down into your shaders. Yep, we got operations inside of mv.js that'll take care of doing all that for you. Like here, multiply these matrices together, I got 1, stick it into a uniform, call it a day. So there's your performance tip. Now, how do we actually send the angles from the application? Well, remember, those are uniform variables, so we need to update that part. So we create a little array here called theta, and the axis variable that we've got. Get the uniform location for theta, and put that into a variable called theta location. Right? This is the value we're sending into the shader. This is the index that's associated inside of WebGL with this variable string inside of the shader itself. So then down in render, we update whichever axis we're rotating around. That's what this little guy is, the selector inside of here. And then we load into the location our 3 angles that come in here. So we can update X, Y, and Z. Numbers get updated, and the uniform call sticks them down in the shader. Then we do all that fun magic that goes along with it. So that said, we'll move on to the next part, lighting, which actually uses a lot of these kind of things. I'll take care of this. You do texture mapping? Yep. I like lighting because it's illuminating. Yeah, I know. It's getting late in the afternoon. We got to talk about those things. So what does lighting actually do? We're going to talk about very rudimentary, simple lighting, something that's easy to get your head around in a shader. We don't want to assume you guys are, you probably understand BRDFs and can do light maps and all this kind of cool stuff. We're going to talk about something that's 20 years old that was really simple and easy, and it's nice because it makes a good example of how to do things in a vertex shader. But lighting is important, right? It gives you visual clues about stuff. Those two renderings are exactly the same objects, but in one case it looks like a blue triangle and a red circle, but it really is a blue cone and a red sphere. And the only difference between those is the fact that there are illumination clues that kind of go, oh, right, it's a shiny red ball where the sun's or the light's coming from over there. It's the same thing there, it's just not a shiny red ball, it's just a very dull red ball with no reflective properties. So lighting gives you intense amounts of information. How do you do this? Well, this is all done by computing lighting in the vertex shader. Now, what we do is we take a lot of different attributes that are computed or that are provided per vertex. Remember, a vertex is a little bundle of information, so part of that bundle we stuff in all the stuff that's necessary to do lighting. And there are a couple of things that go inside of there. One is what's called the surface normal, and I'll describe that more in detail in a second. There's a bunch of other things like what are the colors that are going to be responsible for specular and diffuse reflections. Inside of this model, there's basically three modes we work with. One is called basically ambient. So if we were to turn off all the lights in the room, the light that you see inside of the room is the ambient light. It doesn't come from a direct source, right? It peeks in from under the door or leaks through the wall or any other opaque object you might have. But you can add it into the scene, right? Ambient light normally is gray. You've got the diffuse color of an object. Diffuse color of an object is the color you see when you look at it, right? The drape under the projector is black. The carpet is blue, right? The first color you perceive is diffuse color. Specular is the color of the highlights that are on top of it. So, for example, in the red ball, you saw a white dot. It's got a white specular reflection. So this model combines all those things together. It's patterned after what was in the original OpenGL. It's called the Phong lighting model. It used to contain a term for emission, and emission was just an additive color that went in there to make something look like it glowed. The model's pretty simple. Basically, you can keep adding colors till you get to white, and then after white, you get nothing more. So you can't have a white ball with a red highlight. You have a white ball with a white highlight that's saturated, or a red highlight that's saturated to white. So there are limitations to this, but it makes a nice example. So the way we do this is we compute the lighting value at a vertex, and then we pass that information down into the rasterizer, and it's interpolated across the primitives. So let me go through the constituents of how this goes. The first thing we need is a surface normal. A surface normal is a normal that's connected to a vertex and says, if you were to put a little mirror at the vertex and put the normal, basically the perpendicular that mirror, pointing in the direction of the normal, that's how light reflects off that particular point. So we use this to basically determine, is the vertex in the line of sight or not? Is it in the front of the object, in the back of the object? Those kind of pieces that go along with it. It's nothing more than adding another 3-valued vector to the position of a point in space. Easy enough. I like spheres because it turns out if you use a unit sphere, the vertices are exactly the normals, or put another way, the normals are exactly the normalized vertex values. Really convenient, nice thing to learn with, so that's what I did here. Nice picture. So this shader that we put together pulls in a whole lot of data. Now, some of the things that we have, this is not a WebGL shader.
Oh, you got the wrong version.
As I mentioned, Ed went out and had a few libations for...
The version we didn't have, I changed it.
Forgive us, there is a mistake on the slides. This is an OpenGL shader, but WebGL and OpenGL very, very close, except this is a kind of more modern OpenGL 4 shader. To get the one to port to the other, you need to take the in and convert the word in to attribute and the word out to varying. Now, in modern OpenGL, since we have the opportunity to discuss it, they have many more shading stages. They've got vertex shaders, they have what are called geometry shaders, they have tessellation stages, and more specifically it goes vertex, tessellation, geometry. And because you had attribute and varying, well, now we have too many things to actually get all those to fit together, so they made it a little more simple. In variables go into a shader, out variables go out into the next phase. That makes it pretty simple. I'm sure eventually this will wind up in WebGL as well, But for the time being, just think we've shortened attribute to the word in and shortened the word varying to the word out. All agree on that? We're good. So these are all of our uniform values. So we have these different things called the ambient product, diffuse product, and specular product. All that is basically it's the color of the light times the color of the material put together. And we do that in the application because it's not going to change, right? The light has a single color, the object has a single color, and we put those together. We have our model view matrix and our projection matrix, a vector which represents where the light is, another value called shininess, which I'll show you how it folds into the math. So that's just all our variables. And we feed a couple of attributes into the position and the normal, and we generate a color. And that's all lighting is doing, is generating colors. Now we do a whole bunch of stuff. One, we take the position and multiply it by the model view matrix. We take the position and modify it by the model view matrix, and then carve off the x, y, and z values. And you're going, huh, what are you doing? This takes and converts the vertex position and puts it into I space. Now, these are all homogeneous coordinates, right? This is a vec4, 4x4 matrix. So we get a vec4 at the other side, so we pull off the first three coordinates. We could have equally taken this off and put .xyz here at the back and done the same thing. Why? Because we wanted a vector in this particular place, and we call that our I position just pos. And then what we do is take the light's position and subtract from it the I's position. And what does that do? That gives you a vector that goes from the I pointing out to the light. Okay. We normalize that. So because we're working in I coordinates are when the I is at the origin looking down the minus z axis. So this is our line of sight vector. It takes the position and looks down the minus z axis. Yes, this is a slightly optimized one, slightly not as educational, but you get to see the kind of tricks that you'll see in production shaders that people use. And then we normalize basically the lighting vector added with the line of sight. And basically what that does is take the dot product and figure out how much down the lighting vector the line of sight is. Are we looking directly into the light, or are we looking away from the light? So that's what that guy is measuring. Now, the next part, we take the lighting normal and normalize that as well. So we transform that into I space, take and multiply that by the model view, chop off the top three coordinates, and we get a new vector that's been normalized. So that's unit length as we go through. I know this is kind of fast, but if you take a look in any graphics textbook, it'll describe this process in great detail. So we take and compute the ambient color, we just assign that to ambient, right? It doesn't come from light, there's no reflection in the object, it's just light in the scene. So I stick that there. We compute the diffuse coefficient, so we have the diffuse color multiplied by this funny equation. We take the light's position and dot it with the normal. Now, you remember I said the normal is like a little mirror and says how light reflects on it. So if that little mirror is pointing directly at the light, you get full intensity reflected back. That's when the dot product of two vectors that are coincident. You get a value of 1. If the mirror is pointing directly out of the way of the light, you get a dot product of 0, right? They're at 90-degree angles. So that actually controls how much of the color of the object you see based on direct illumination. So we do this, we clamp it to 0, so you can see a little bit more. We have a dot product vector, and then take the max of that value in 0 if we happens to be two vectors pointing that give you a negative value, and use that to modulate the diffuse value that comes into the shader. So this gives us our diffuse color. This is kind of a similar complication. You've got H, which is something called the half vector. Effectively, it's the vector between the I's point and the light. It's the vector halfway in between, and then we take the dot product of that with the normal. And this gives you more clues about the specular part. So the math here, you can look at it and go like, what's going on? This is the same dot product of two vectors, it's just one of the vectors is slightly more special, because the specular highlight depends on where your eye is located. If you go look at a shiny car, like across the street is a bunch of Ferraris, if you go look at the nice wax job on them and move your head, you'll note the highlights move. Why is that? It's not the cars moving, it's not the sun moving, it's because your eye's moving. So these highlights need some dependence on the eye's position. And this H vector, which we computed in the previous slide, actually takes that into account. So this is the same kind of thing to compute this value, except the shininess, specular highlights are measured by what's called shininess, the smoothness of the object. So if you imagine a really smooth ball, highly polished, the specular highlights are almost a direct reflection. They're really, really tight. But if you look at specular reflections on a rock, rocks are kind of rough, right? So it kind of spreads out on that. So shininess is just a way to simulate that kind of thing. So we generate that and make the specular color that goes along with it. Now, we do one extra thing here. If the object is well, basically, if the vertex we're working on has a normal that's in the opposite direction of the light, that is basically on the opposite side of the object, we don't want to highlight on that side. OpenGL, WebGL, OpenGL ES are all rasterization-based libraries. They don't know anything about one primitive or another. Each one is done in isolation. So if you think about drawing a ball, right, you never see the backside of a ball. You know, you have to get your friend to look and verify that it's there because you can never see it, right? GL doesn't know that, right? GL basically looks and goes, I've got a whole bunch of primitives that form this thing. You think it's a ball. I think it's a collection of triangles. I'm going to take and rasterize each triangle as I get them. So the triangles that are closest to you with the light behind you should have a specular highlight on it. The ones on the other side of the ball should not have a specular highlight. Now, because we can control the viewpoint, you've got to be careful about this. So this particular bit basically says, okay, cut specular highlights off on the back half of the object. If you can't see the backside, we're not going to at least put a shiny spot on it. We'll still put a diffuse part there. So that's just a bit to make to make it look a little more realistic. What do we do then? Well, here we set up our GL position. Position times model view times projection spelled out very nicely here, and compute our color. Specular, diffuse, and ambient all added up. And then we use one of those selectors set the alpha value to 1, right? Because there might have been additional alpha values inside of there. Somebody's trying to make a transparent sphere. We just set it all to 1 and get it done. So I know that was a lot of math inside of there, but it gives you a nice idea of, you know, this is actually a fairly complex shader. And if you had to write it in C, there'd be lots of for loops and other things. Writing it in GLSL, a lot of the operations that you want to do are very nicely expressed. Take the dot product between the light and the normal. Well, dot of L dot N. Okay, great. And make sure that doesn't go below 0. It's very easy to put it together, and you can see how it all accumulates. So that's kind of the magic behind it. The next part, now this is a vertex shader. And so what that does is compute lighting at the vertices and has the rasterizer interpolate. That's what's actually called Garot shading. Garot shading is the name of when you interpolate colors at the vertices. There's another mode of this, which is called Phong shading, where you actually compute the lighting color at each pixel as you go along. If you take all this math out of the vertex shader, stick it into the fragment shader, patch up the variables enough to go, oh, I'm not going to iterate the position. I'm going to pass that down into the fragment shader. I'm going to pass the normal down into it. You can actually compute your lighting per vertex. You get incredibly better results with identical math. What did I say? Yeah, fragment, sorry. So this is really nice because you can see how lighting works at the vertices, and to get really nice results, you have to really tessellate an object, have a whole lot of vertices. Or you can take the same math, stuff it in your vertex shader, and go off. Why is that? Because everything except for this line here in the shader is about color, setting up a color. Fragment shaders, their only job in life is to figure out a color. So that's why you can take and translate it. So Ed's going to talk about the next section called texture mapping, which is all about generating colors. So, hey, go nuts.
And there are examples of all of this on the website of doing it per fragment. And one of the things that actually, if you think about what Dave was just talking about, if you're doing the per vertex shading, you could have had the option of computing that in your application and then sending the vertex colors over. But it's just, again, using the power of the GPU to let the shaders compute it. And then when you're doing it per fragment, not only is it visually better, but depending on your GPU, it may actually even be faster. That's a little unclear depending on your GPU. But there's examples on the website that'll show you the difference in terms of the shading. What I have is an example of a tessellated approximation to a sphere. And if you do not too fine a tessellation, you can really start seeing the difference where if you do per fragment shading, it looks very, very smooth, and you don't have to tessellate it to as high a degree as you would if you do per vertex shading. And again, all of those examples will be on the website. Okay, so the final part we want to talk about this afternoon is texture mapping. And one way to look at texture mapping is what you're trying to do is avoid what's called the geometric complexity of generating more and more geometry and more vertices. And no matter how fast we make our GPUs and our computers, people will come up with more and more complex geometry they want displayed. So one example that's we like to use, sort of a classic example, is if you wanted to make a model of an orange. You know, what would you do? Well, you could start off with a sphere and color it kind of orange, you know, the fruit. And that wouldn't look quite very good. So you say, well, what is it that really makes an orange look like an orange? Well, there's a lot of structure there. There's all the dimples on the orange. And you say, well, gee, if I have to start modeling all of those little dimples, then to get this one orange, I'm going to need an awful lot of geometry. And so we say, well, we better look at some other kinds of techniques. So one would be to take a picture of an orange and actually paste that picture on it. So it's sort of like if you see a three-dimensional picture on a soup can, that's a texture map. It's taking a picture, and instead of having all the geometric complexity of what's in that picture on the nice can in the store, you're replacing it by taking a two-dimensional image, having a simple geometry, and just wrapping it around. And where does this happen? It happens where we set the colors in the fragment shader. Okay? So that's the basic idea of texture mapping, the complexity of texture mapping. There are many forms of it, but the complexity is actually how do we set up these maps? I mean, how do we decide for a point on our object or even a point on the display, what point in the texture map or the picture does that correspond to? And that's what we'll see how we do. Well, and basically what WebGL and OpenGL does is say, it's up to you. We're not going to figure that out for you. You tell us where you want it to be. So let's go through that. So here's the basic idea. You start off with your geometry, and here my geometry, I don't want to burn myself. Here we go. So here our geometry is just a little trapezoidal, almost rectangular. You know, we've just sheared it a bit. And what I want to do is put all this picture onto it. So one way to do is say, well, you have a couple of coordinate systems here. You can describe this image, and we'll just deal with rectangular images here, and say it has its own coordinate system. So this is the ST system in 2 dimensions and the STPQ if we go up to 3 or 4 dimensions. But actually, WebGL only does 2-dimensional texture maps. So it's the ST system. So I could say, and we'll say that we're going to normalize things. So S and T are both going to go between 0 and 1. And so for any values of S and T between 0 and 1 will correspond to a point or a texel. Instead of calling this pixels, we tend to call them texture elements or texels. Will give us a location and a texel in that sampled image. So what I want to do what I need now is to know for a point on the display, one, what point in the original space, the world space, object space was that, and then what is the corresponding point to get the texture from. Okay, so that's the basics of texture mapping. Well, how we do it is now, one thing to note is that where this all happens, that it doesn't affect the geometry. You don't need the texture until you're really ready to set a color. So one way to think of this is that we have this pipeline architecture, but really there's 2 pipelines. There's the geometric pipeline that we pass through, where we go through the vertex shader and then off to the rasterizer, and we get values that go to the fragment shader. But that's where we need the colors from this texture. And so there's sort of a separate pipeline that's much simpler that goes along here. Now, there are things that happen here that we're not going to talk about that have to do with, what is the format of the image? Do you want to rescale the colors? Do you want to do varying other things you might want to do? Issues like what's up and down, depending on how you got the image. It may come in a flipped format. There are functions to handle all that. But basically, what's going to happen is you're going to put in an array, a square array of texels or pixels, and they're going to go down some pipeline and be available to the fragment shader. Okay, so we can start off with a very simple way of doing it and saying there are 3 basic steps which we'll expand on. One is, specifying that image that we're going to use, assigning it, we'll see, to a texture object. Actually, we don't have to enable it. This is more, it's automatically enabled in WebGL, correct? Texture mapping is automatically enabled. I don't think I have to. Yeah, we don't have to even enable it anymore. Then we have to say, okay, the way that we're going to do the mapping is say, we in our code have to say, what texture coordinate corresponds to the vertex, to each vertex. So again, it's another vertex attribute. So just as a color might be a vertex attribute, a normal might be a vertex attribute, the texture coordinate is a vertex attribute, and that's your job to do in your code, to make that assignment, and hopefully the geometry is simple enough that it's an obvious kind of map. And then we have to specify a bunch of parameters. So there are issues like what happens if the texture coordinates are not in the range 0 to 1? Do you wrap them around and modulate them? Do you clip them at 0 and 1? What do you want to do? There's an issue because even though we think of the texture coordinates as being continuously going between 0 and 1, they refer back to a discrete entity, which is an array of picture elements or texels. Well, anytime you're referring to something discrete, you have the problem of getting aliasing errors, jaggedness that comes in. So some of the functionality that's supported in WebGL is that it allows you to do filtering or smoothing. That's generally now built into the GPU. You can either take a point sample and then have some jaggedness, or you can do some sort of averaging of neighboring texels to get a smoother image when you get out. So those are parameters that we have to set when we set up our texture. Now, the way that this is done now in WebGL, and certainly now in all modern versions of OpenGL, is to use what are called texture objects. The problem initially used to be that you could have only one texture and it was the current or active texture, and every time you wanted to change it, I mean, imagine having our cube and every surface has a different texture on it. What would happen is you'd have to load the texture back in and you'd have this enormous bottleneck going between the CPU and the GPU. So when we created texture objects, the idea is that the GPU has a lot of memory available to it, and we can store multiple textures in the memory available to the GPU on the graphics card. And so we do this by having what are called texture objects. And the texture object consists not only of just the texture image itself, but what collection of parameters we want to apply to that texture. So we create a texture object by a create. So it's very much like vertex buffer objects and the other things that we've seen. We do a create, we do a bind in order to make it the present texture object that we're working with. Right now, only texture 2D is supported, but in the next version of WebGL, you're going to get 3D textures, which are a very, very powerful thing to have. And we now put into that the parameters, but the fundamental one is what does that texture image look like? So we're telling it here, it's a 2D texture, it's RGBA pixels, it has a height and a width, it's stored as unsigned bytes, and the data is in an array called image. Okay, so there's the information to describe the texture itself. We have a couple of ways we can do that. We can assign it say, well, where'd that image come from? Well, we have choices. We can generate that image by code if you want some nice regular pattern, or you can use HTML. So HTML has an image element, and we could use the image tag in the HTML file, assign it an ID here, text image, and then just use it as we have here. Or you can, well, that's generally the easiest way, is to just use the image tag in the HTML file. Okay, now what does the mapping look like? Well, this slide really shows you, I think, the most of what we're trying to do. So here's your texture, and suppose our texture image has this sort of brown, this magenta, and this blue part. This is what the image looks like, and we're thinking of it now as being continuous. And what I want to do is map that texture somehow to a triangle, okay? Because, well, that's what we deal with. We deal with triangles in WebGL. So I have 3 vertices that define that triangle, and what I need to do is say, well, what are the points inside of this square that goes from 0, 0 to 1, 1 that correspond to vertices A, B, and C, and that's what I have to do. So I say, okay, well, if vertex A is 0.2, 0.8, that's its texture coordinates. That's this point over here. Likewise, if C is 0.8, 0.4, that's this point over here. And if B is 0.4, 0.2, that's this point over here. Well, those 3 points determine a triangle. So that says what's going to happen when we do the texture map. And this, again, involves the rasterizer. Where do the texture coordinates go? They go through the rasterizer, and they're interpolated. So they're interpolated to give me a texture coordinate for every fragment. And that's what's passed on to the fragment shader. So all of these values in this little dot dash triangle here are going to be spread over this triangle. Okay, we're not showing any of the jaggedness or the aliasing. We're assuming it's continuous here. So if I had assigned different texture coordinates, I would get a different triangle here inside of this square, and I would get a different pattern over here. But the process is fairly easy to understand. Once you've chosen your texture coordinates, it's all happening automatically because the rasterizer is going to interpolate that to get our texture coordinate for each fragment. Now, how is the texture applied in the fragment? Well, that's pretty straightforward through something we haven't talked about yet, which is called a sampler. So a sampler is what you would think. It goes back. You give it a pair of texture coordinates, you tell it the image, and it goes back and gets a sample of that image. Okay, that's what a sampler should do. So here's the fragment shader. So again, we have to have a precision statement. You can combine a color with the texture. In this example, I'm multiplying the texture by a color that I computed either by giving a fixed color in the application or using a lighting model. It's sort of what you would have if you're trying to simulate glass that wasn't smooth. You would have a color of the glass, and then you'd also have the texture of the glass that would give it a more modeled appearance. Or you can just simply have the texture totally determine the color on the output, in which case I wouldn't be passing in this color. I would just have the fragment color was equal to the sampler value. That would be sometimes called decaling, where it's like pasting the soup can cover with just a picture. But it's all, essentially simple and the same. So here in this example, I pass in the texture coordinates as a varying variable interpolated by the rasterizer. I pass in a color from the vertex shader, again interpolated by the rasterizer. I have a sampler value here which refers to the texture object that I set up, which includes all the parameters I want to associate with that texture plus the texture image. And then it's just one line that the output is the product of the color that I came in from the rasterizer with the sampled value of the texture. So texture mapping at that level is very, very simple, but it's also very, very powerful. And here's just, again, the little piece of the code. So here would be a little piece of the corresponding code in the application. If I'm doing this to our rotating cube, I would be pushing vertices for each location. I'd push a vertex. I have another array for the colors I'd push, and I'd push the texture coordinates. So it's not much of a change to the code that we've seen so far, and I do that for each vertex. Okay. Here's an example where I like to use this example. It's a checkerboard texture. You can, again, all this code will be on the website. It's a good example because one of the things that happens with texture in practice is that the sampling and aliasing problems can really be serious with textures. You can get these jagged effects, these moire patterns arising. So one of the ways to really do a lot of testing, and I think there's a good example on the website, where I generate some rectangular patterns, some checkerboard patterns, and you can move them around and you can see how the different options affect the texture that you're going to get, the various filtering options that you can do. So here's just something that'll generate that image for you. Here's an actual texture object where we create, which has some of the parameters in it. So let me go through some of these. So we create a texture. We set now in textures, one of the things that all versions will now do is support texture units, where you can now have
texture 1 applied, followed by texture 0 applied, followed by texture 1, followed by texture 2, and there's a fair number minimally that each implementation has to support. So now you can get multiplying effects of textures. So this says, okay, I'm going to be talking about texture unit 0, the first one here. I bind that, so that's the present texture that everything now will apply to. Since I'm bringing in an image, I have to flip it over. In general, there's a problem we haven't talked about, that there's sort of a disparity historically in the literature, that images that sort of come out of the display world are displayed from top down. Images that come from the engineering and science and mathematic worlds put the origin at the bottom left, so they're displayed up. And so you'll see, if you aren't aware of this, things will be upside down. So one of the things you can do is automatically flip things. This comes up also in interactivity. Anytime you're getting the mouse input will actually come in upside down from the way you want it, so you automatically have to flip it. So here's a parameter that just says to automatically flip that image coming in. Here's the texture image again, given the size, it's an RGBA image. Now here we're generating what are called mipmaps, and let me just say in words what mipmaps are, is if you have a texture is a lot of memory and it's a lot of work applying this texture. And especially if you're dealing with perspective, you can have an object, and if it's far away, when it's displayed, it only occupies a pixel or two. Well, if you have 1,000 by 1,000 textures map for that object, you don't want to have to go through all of those million points in order to get what's just a pixel or two on the screen. So the standard way to get around that is to use what are called mipmap textures. And what you can do automatically is generate a family of textures, a hierarchy of textures at sizes. So if you start off with a 1024 by 1024, you can automatically, through generate mipmap, will automatically generate a 512, 512, a 256, 256, and down till you get a 1 by 1 texture. And the implementation, when it does the rendering, will decide what's the most appropriate one to use. So that will save you lots and lots of time in your rendering. There's some, again, the example on the web will give you that as one, and you could see where in this checkerboard image, as it's a perspective image, so it converges, you can see where it's flipping between textures at different resolutions. So that's something you might want to look at. And here's some of the parameters. What do you want to use filtering here? It says if you're on your minification, you have magnification and minification. Here it's doing a linear filtering. Here it's just saying take the nearest value when you to the texture coordinate in the sampler. So you can also have filters which are there it is. This one is using mipmap and linear filtering. You can use linear filtering alone. You can use mipmap alone. There's a variety of these parameters that you can pick, and again, they're part of the texture object. Okay, so vertex shader is pretty simple here for this example, because all the vertex shader is doing is passing them through. It's saying, okay, here's the texture coordinates coming in as attributes, and all I want to do is send them on to the rasterizer to let them be interpolated for each fragment. So it's a pretty trivial, so it's essentially the trivial shader, vertex shader we had before. All we're doing is adding texture coordinates to it. Okay. And here's again the fragment shader, but for doing that. So that one's pretty straightforward. Now we're actually pretty much on time. So let's say a few things, and we can have a little time to answer some questions, and we want to give you a few resources. One of the things we haven't talked about that's really powerful in OpenGL and is in WebGL is off-screen rendering. The idea of rendering to texture, so that you can do a rendering and keep that rendering by rendering it generally into another texture. Then you can come back and use that texture for the next rendering, which renders into another texture. So you do what's called buffer ping-ponging. You're going back and forth, generating new textures. The new texture is used to generate the next image, and so on. That is an incredibly powerful technique You can do it for all kinds of applications that are not, that at first don't seem like they're geometric applications at all. I have an example I can show anybody's interested after that, where we're doing a lot of simulations, agent-based models of saving the information as things move around. Just think about if things are moving around and you want to save them, how do you save them? You can save them in texture. Or another way of looking at this, and this is opens up whole other areas, is the basic problem when we talked at the very beginning about we didn't talk about it much, is the idea of a ray tracer and doing what's called global rendering. Is you want to have everything available. That's the nice thing about the pipeline models, are that everything gets rendered. It goes into the pipeline, it comes out. It doesn't really care about anything else except for some tricks like using the Z buffer. But what if you want to store some information? What if you have like a particle system and you want to store where they are and you want to store where the neighbors are? Texture is shared memory. Texture is the one thing that you have available to you in OpenGL and WebGL that really provides that kind of stored memory. So the ability to have multiple textures, to write into textures, and then read those textures and use them just opens up all kinds of new possibilities. And from compositing comes in there. Cube maps is another form of texture mapping. Where, as Dave said, you can actually do things like have 6 texture maps. So if you wanted to say, do something in this room, you could have a texture map for each of these walls and then use that as part of getting an accurate lighting model that brings in the complexity of what's really on these walls. So rather than try and simulate all these lights on the ceiling, what I might do is have a texture map that has all of these lights in it. So all of these are things that are very nice extensions. Again, I refer you to the website where you can see a lot of these examples. So finally, let's say a couple of things about resources. We do have a new edition. Well, Dave's the author of the Red Book, the OpenGL Programming Guide, which if you really wanted good program, it's a good programming guide, and it has, if you want to know about one of the many OpenGL functions, it's in there. There are a couple of guides for OpenGL ES. There's a new edition for the OpenGL ES3 just came out. There's a bunch of, there's our book, Interactive Computer Graphics, which is a textbook that's pretty popular. It's in its 7th edition, just came out. And we switched to WebGL because we're so excited about this as being just a way better way to learn OpenGL and do graphics. There's a couple of other books. There's the OpenGL Super Bible. There's a couple of WebGL programming guides out there. A lot of these books are just coming out. I saw another new one at the bookstore today. And then there's a bunch of related books. Some of these are getting a little old about OpenGL programming for the Mac, OpenGL and the X window system. But if you're OpenGL programmers, some of that may still be relevant to you. And as we said, the present WebGL is based on ES 2.0, and Dave is one of the co-authors of the ES 2.0 programming guide. The ES 3.0 programming guide just came out, and there's a draft standard for the next version of WebGL, which will be based on ES 3.0. Okay, and there's a whole bunch of web resources out there. The one down there is my website has a lot. If you want to know if your browser works, this getwebgl.org, if you just go to it and it'll display a little rotating wireframe cube if your browser supports WebGL, so you can test that out really simply. But if you want to really see some of the really powerful demos, Chrome Experiments is one under WebGL. There's some incredible demos on there. And the other is Shader Toy. There's a website, it's shadertoy.com, which has just unbelievable examples of what's possible with shaders. So a lot of stuff keep coming out. Chronos sets the standards. You can get the standards information off of them or from the OpenGL website. So let us stop here, and we're happy to answer questions. Dave, you have anything you want to add? Or? So thank you all for coming. And here's our contact information.
Now that I think about it, so Ed mentioned the Shader Toy website, which is really, really exceptional. The guys who do that are putting on what's called a Shader Toy Hackathon. They're doing a kind of 2-hour intensive class of like, here's the website, come in, play with WebGL. One of the guys is I think a TD shader guy at Pixar. The other one works at the game company. The kind of things that come out of their shaders are amazing. And it's really, really approachable. All the events of the conference are kind of blurring together, but I believe that's on Wednesday at lunchtime. Check your conference locator. But that would be a really cool way to see the kind of things that are available. And in that particular environment, the vertex shader transforms a quad, and that's what you get. Everything is done to fragment shader. And while that might not sound too impressive, go to the website and take a look at what some of the things these guys have done. Interactive applications where cars are driving, planes are flying, they've got things that reconfigure themselves, ray tracers. It's really, really cool technology. I went to it and I was like, yeah, I thought I knew something about graphics. I'm just going to leave now. So, I mean, the stuff is really good stuff.